Hi, I'm Cullen. Welcome to Networking Fundamentals. This is Mod 1. We're going to focus on understanding local area networks. Thanks for joining me. Really excited to teach you about networking. Let's get started. Quick overview of our agenda. We're going to discuss local area networks, talk about data transfer on a local area network, also known as a LAN. And we're also going to feature the different types of local area networks that you might come across. All right, local area networks. So first, what is a network, right? A network is just two devices that are connected to each other with a physical medium, like a wire cable or a radio signal. This picture here, just a wired cable, like an Ethernet cable. The connection allows two devices to just exchange data back and forth. So there we have some data moving across, some binary there. We'll talk about binary in a little bit. Networks have a lot of different purposes too, okay? They're used for communication and collaboration inside of a business or an organization. They allow us to share information and resources like text and tweets. They make it possible for us to organize data. They also allow us to save a lot of costs because we can share resources like printers and other different services that are available through networks. All right, so how are networks organized, right? Like we have all these devices around the world. How are they organized with one another? Not just around the world, but also inside of the same building. They're organized based on their geographic location or where they are in the world, in a building or in a city. A local area network or a LAN is simply a group of computers or devices that are featured in the same small geographic location, right? So like a school or a small office. They all share a common communication medium. So, you have cables like we talked about earlier, or also wireless connections. They're also connected to something called a central connecting device, which we'll detail here in a little bit. Those can be hubs, switches, or routers. All devices that are very important to learn about. Network documentation, I guess. If you're designing a network, you have to define and describe and explain how different devices on a network are connected, right? We want to know the physical location of each of the devices and also how they're connected logically, like the general design, right, that we have up in our brains. The documentation phase occurs before you actually build networks or whenever you make changes to a network. And I just want to highlight Microsoft Visio as a tool that can be used in order to design networks on your PC or on your laptop. All right, so what devices make up LANs? We've got hosts, right? Your phones, laptops, desktop PCs, servers, and tablets. We also have central connecting devices, which are hubs, switches, and routers. We typically interact as users with host machines. Those host machines then connect to central connecting devices, which are responsible for relaying our data to other host machines. Hosts, we already detailed the different types that are available, right? The different kinds that there are. But a host is defined as any device that has something called an IP address. An IP address is used to send and receive information. It's very similar to your mailing address for your house. Pretty good way to remember what an IP address is and what its function is. And IP addresses help identify not only the device, so like your house, right, but also the networks where they're located. And if we go back to that home address analogy, a network would be sort of like your city or maybe even your street block. Central connecting devices, as I mentioned previously, are for connecting hosts and also transmitting data. Different central connecting devices, they perform these functions in different ways. And I'm going to show you, model for you those different ways here in just a second. Okay. First, we'll get started by talking about hubs. Hosts send data to a hub, and then a hub then broadcasts that data to any other device that's connected to it. This is sort of an antiquated technology. It's old and becoming more and more obsolete, if it isn't entirely obsolete already in most parts of the world. But what happens is it is going to so this computer, this device, like you just saw in the demonstration, sends its data, and then every other device that's connected to a hub is going to receive that data. The difference, though, or rather a potential problem here for us, is that this computer may only want to send data to this laptop down at the bottom of the screen and not to the server that's located up at the top right. We're able to correct this problem with devices called switches. And unlike hubs, switches send and receive data simultaneously, and they also send it directly to its intended destination. So take a look at this example here on the right. Okay, so you've got data being sent simultaneously, not even necessarily between two different devices, but amongst different devices entirely, and they go specifically to their intended target. So you saw the yellow piece of data there go from the PC to the laptop, and you saw the turquoise or green piece of data there go from the laptop to the server. Okay, and switches, I guess a good way to summarize it is switches are just simply smarter than hubs. Let's talk about routers. Routers are at the edge of a local area network, and they're the devices that are responsible for connecting us to the internet. Okay, they act as a gateway to other networks. Okay, routers allow communication between hosts on different local area networks. So we can actually connect to local area networks via a router, and that's actually how you make up the internet, right? You connect a bunch of local area networks to each other. Here's a quick example of that data going out to the internet. Pretty cool stuff, right? All of these devices connect to each other via network adapters, right? Network adapters are also known as network interface cards, and these are the pieces of equipment that make it possible for computers and even our cell phones to communicate with each other, right? NICs communicate via wires or wireless signals, and this guy right here, this wired adapter, it features something called an RJ45 port. Wireless adapters feature an antenna in contrast, and they connect to networks using wireless access points, which are, they're also essential connecting device, and we'll detail them a little bit later in a different module. Of course, if we go take a look at our RJ45 port, we have to have something that we can connect that to or connect that with. And what that is an Ethernet cable, right? Ethernet cables are made of copper wires. They transmit data in the form of electrical pulses. Okay, wireless communications, they rely entirely different technologies, radio signals. Okay, so keep in mind that copper cables transmit data in the form of electrical pulses. You may have heard me mention binary data earlier, and electrical pulses, if there's a pulse, it might represent a state called on, and if there is, so let me write pulse here real fast, and if there is no pulse, then that represents a state called off, all right? We normally say a pulse would be like 1, on would be represented by a 1, and then no pulse would be represented by a 0. And that is called binary. I apologize once again for my atrocious handwriting. So here we will talk about wireless access points just a little bit. They provide a central point of access for laptops and cell phones and even PCs and households, right? We can wirelessly transmit data to these wireless access points, which are actually connected to switches and to routers, right? So even though we access a network wirelessly, that data still is transmitted across a wired network, which I think is something that's super interesting. I'll just point out that little wire there. All right, so now let's switch modes and talk about data transfer on LANs. Data is transferred through serial data. Data is transferred in a serial format. So that means 1 bit of data at a time is sent. Now data can travel in a single bit stream in both directions, like to and from. And how it does that depends on the type of connection. And you've got a couple of different types of connection. There's something called simplex, which is like a one-way street. So data can only transfer from one device to another. Whereas we also have something called duplex, which is like a two-way street, which means that the data can be sent and received at the same time. There's also another format called half duplex, which means that you have 2 streets, but only one of them is in use at any given point in time. Okay, so data can only be sent to and then also sent from, but not at the same time. Okay, all right, move on to the next slide here. The speed that data travels is measured by bits per second, right? That's called its data transfer rate. So we signify this data transfer rate as in, we've got the number there, so 10, right? And then M, which in this case stands for mega, right? And then we have a lowercase b. This lowercase b is a little bit different from the type of data that we store. It represents bits, right? Not to be confused with a capital B, which would represent bytes. This whole construct down here, right, is called the bit rate. And we use that to measure how fast data transfers over a network. So before data is transferred, it actually goes through this really interesting process, right? We break large chunks of data into things called segments, okay? Addressing information is then wrapped around that segment, and we call it a packet. From there, we then add a little bit more information in order to make it something called a frame. And then each frame is broken into the bits that we see on the screen. This visual might be a little confusing, but just know that really data is ultimately going to be represented in bits before it's transmitted across a network. So this whole thing ends up taking this form right here. And then it's transferred over a physical medium in binary. All right, and of course, when data is received by a device like your cell phone, it goes through the reverse process. So what happens is that the receiving computer is going to go ahead and take all those bits. It's going to read the frame, or rather it's going to reassemble the Ethernet frame. It's going to strip that physical addressing information, and then it's going to strip the logical addressing information known as the IP address. So it's no longer a packet anymore. It's going to come back into its segment form, and then it's going to be reassembled into the file that we click on in Windows Explorer, which I think is a pretty cool process, and it actually really simplifies the way that data transfer occurs. All right, so how does data know where to go? Well, we mentioned IP addresses, right? Those are logical addresses that uniquely identify a device and its network. So an example here would be 192.168.1.1. Every IP address is broken down into 2 different parts by something called a subnet mask, which we'll detail here in a little bit. And so we have a network ID portion, which is 192.168.1, and then the host ID, which is 1. This network ID, think of it as like city and state, I guess maybe your street name. And then we also have the host ID, which would be like your house number, right? All right. Another thing that's really worth mentioning is that IP addresses, the way that they appear, note these little dots that split up the different numbers. Those separate octets. We'll detail IP addresses a little bit more later, but octets actually are just 8 bits. And there are 4 octets in an IP address, which means that an IP address is 32 bits, so 32 zeros and ones. Like I just said, we're going to go ahead and touch on the subnet mask now and detail that a little bit more. A subnet mask is just a group of 4 numbers that define a computer's network. All right, so if you look down here, 255s represent the network portion of an address. So 192, 168, and 1, just like in the example that we just saw. Okay, and then a 0 is going to represent the host portion. So if I change my slide color, or sorry, my pen color here, this 4th octet is the host portion, right? So that's like our street address. In contrast, over here, everything that is represented by a 255 is going to be our network portion. This is really important for us to keep in mind as we're learning this. We'll revisit it throughout this course. All right, so finally our last little objective for the day, types of local area networks. Wired LANs come in different forms, right? And we have these wired LANs where each PC is connected to a central connecting device, whether it's a router or a switch, via an Ethernet cable, right? A copper-based twisted pair cable, in fact. We also have our wireless LANs, where each of our devices are going to connect to a network via Wi-Fi signals, right? Radio signals that transmit data ultimately onto a wired network. And finally, we also have a very special type of LAN called a virtual LAN. Virtual LANs can be wired or wireless. In this example, they're all wired, right? And VLANs allow us to group devices based on their functions. So in this example to the right, we've organized our computers on our network based on teachers and students. So I've tagged any data that comes from the VLAN 30 teacher computers with just a little bit of information, a little bit of data that says, hey, these computers can communicate with each other as if they are on the same physical network. If VLAN 20 tries to communicate directly with VLAN 30, if those devices try to communicate with their counterpart devices, then it's going to be treated as if they're on a separate network entirely, right? So do keep that in mind. We'll detail VLANs a little bit more later on in the course, but super important to keep in mind, right? Also, physical location of these devices doesn't matter at all. Where they're located, these two, you could have two devices sitting right next to each other, but they can be treated as though they're on completely different local area networks. It's a really cool technology and something that definitely makes it a lot easier for you to manage a network and potentially even keep some devices more secure than others, or provide different sets of rights to devices based on their organization affinity. All right, next we'll go ahead and take a look at the following slide here. Perimeter networks. Perimeter networks are really interesting to me. They're also called demilitarized zones, but they're interesting because you have your local area network down here at the bottom, but then you also have your perimeter network, which sits outside of a local area network. And what you do is you typically allow web servers to sit inside of a perimeter network so that people who are accessing your network or resources from your network to access them without giving them access to your local area network. So all of your private devices and maybe even private information of your employees. And you're going to see these typically implemented in organizations and businesses that have web servers or provide hosting for websites or for email, right? Like I said, just to reiterate, the setup allows users outside of an organization's LAN to access those servers and those services, but not the organization's local area network itself. Okay, keep that in mind. All right, so thanks so much for joining me here. We'll just do a quick recap of our agenda again. Covered objective 1.2, understand local area networks. We talked about what local area networks are, just data transfer in general on a LAN, how data gets from one place to another, and also the different types of local area networks. I'm really excited to continue our journey through networking fundamentals again, so I'll see you in just a second in Module 2. Hi, I'm Cullen. Welcome back to Networking Fundamentals. Today we're going to cover Module 2 of Understanding Local Area Networks. Let's go ahead and review our agenda and get started. So we're going to cover Objective 1.5, understand network topologies and access methods. In doing that, we're going to review what network topologies are, talk about Ethernet standards. These are standards that govern Ethernet communications, and also talk about peer-to-peer versus client-server models. So we'll detail both of those models in contrast to one another. All right. Let's move forward. Network topologies. A network topology just defines the physical connections of hosts in a network. And there are multiple types of these topologies, right? We've got bus, star, ring, and mesh. I'm going to go ahead and show you each of those right now and talk about how they function. All devices in a bus topology are just connected via copper cable and a line. So if we have a computer up on the left here, computer 1, if it wants to send data all the way down to computer, let's go, 1, 2, 3, 4, 5 computers, right? So I have 5. It has to send data through computer 2, through computer 3, through 4, and then 5, and vice versa, right? So not the most efficient way to send data. Next, we also have a star topology. It's an advancement over that bus. Each host is connected to a central connecting device, like a hub or a switch or a home router, right? A SOHO router. It stands for small office, home office. And this is the most commonly used topology that you're going to find in an office setting, a school setting, or even at home. Note, though, that you can actually connect two of these star topologies to each other via central connecting devices. And this type of topology is called a star bus topology. So we would connect the central connecting device to another one here that would then connect to computers elsewhere, right? And I'll just central connecting device. All right, let's keep moving. A ring topology. This is one of my favorites to draw if I'm ever in a classroom setting. Each device in a ring topology is connected to another. And note that each device is actually connected to 2 other devices. So if we have computer 1 here, it's connected to computer 5, and then it's also connected to computer 2. Cool. A mesh topology is also pretty fun. One thing that I want you to note here is that there's no central connecting device. This is super important when discussing mesh topologies. This setup also requires that all computers, or each computer, is connected to all other computers within the LAN. So it can be a pretty intensive setup if you're wiring and cabling all those computers and connecting them all to each other. The great thing about a mesh topology, though, is that it's fault tolerant. So if one pathway, if I'm at computer 1 here and I want to send to, let's say, computer 2, if that direct connection between us happens to fault or something goes wrong with it, I can still send my data through multiple other connections. Maybe I want to send it down to this computer here and then back over to 2. I've got different options for sending data to its intended destination. So that's fault tolerance there. And that's part of what makes the mesh topology such a great thing. All right, let's talk about Ethernet standards. So we connect all these computers to each other, all these devices to each other via copper cabling, and there are standards that govern this process. Ethernet simply is that standard, right? It defines how data is sent and received between devices. And it's the most widely used standard on the internet, so it's very ubiquitous. It's used all over the globe. There are a couple of other standards that are used, though. You've got token ring, which each device actually has to have or possess a piece of data called a token in order to be able to send data on a topology. Then you also have FDDI, which is a topology used for fiber optic communication. This Ethernet standard is governed by the Institute of Electrical and Electronics Engineers, IEEE, and it's referred to as 802.3. Devices that use the Ethernet standard transmit frames, and we had mentioned the word frames earlier, but a frame is just a sequence of bits containing a detectable beginning and end. And so here, this is a little cartoonish, and I apologize for that, but I thought it'd be funny if I actually put a frame up on the screen. frames contain physical address information that helps switches determine where to send data. So switches don't actually send data using IP addresses. Switches send data, or they navigate data by using MAC addresses or physical addresses. We'll talk about what a MAC address here is in just a second. First, before we do that though, just a couple of quick notes. This is something that I recall being really important when I took my networking fundamentals exam. 802.3U and 802.3AB are the most commonly used versions of the 802.3 standard. Okay, so do take time to recall that, to remember that, and to lock that information in. And even if you don't, come back and review this slide later on, okay? 802.3 defines something called carrier sense multiple access with collision detection. You'll commonly see this referred to as a pretty lengthy acronym as CSMA-CD. Okay, what happens with CSMA-CD is that devices share a connection, and if they send data, then at the same time on that connection, collisions can occur. And so think of this as if you're traveling down a one-lane road, and you're driving in a car and a friend's driving in a car the opposite direction, so you guys are both driving towards each other specifically, and you couldn't peel off to the left or peel off to the right, you guys would run into each other. That would be a bad thing. That actually happens with data too. And so you could have two electrical pulses run into each other, and all of a sudden the data is corrupted and nobody ends up receiving the data, right? So that text message gets lost because something went wrong. So keep that in mind. Right. Go back to the slide here and take a quick look. The key to remember is that with CSMA-CD, only one computer can transmit data at a time. Okay. Let's talk about this collision, the CSMA-CD process. Okay. What happens is if a computer wants to use an Ethernet network using CSMA-CD, it's going to assemble a frame. It's going to go ahead and listen to an Ethernet cable to see if the medium is free. If it's free, it transmits a bit. And if it's not, then it goes ahead and it goes back and it listens, right? So if the medium isn't free, it's going to go back to checking to see if it is. And then if a collision is detected, it implements something called a collision detected procedure, which we'll detail in just a second. And if not, it just keeps sending all the bits in the frame. All right. So let's check out that collision detected procedure. What happens if there is a collision is sort of like in real life if two cars crash, right? You send out a jam signal and it stops all communication on the medium, so everything just sort of comes to a screeching halt. What happens is the computers or the devices are going to wait for a period of time that's dictated by the number of collisions that occurred, and then eventually, once the lanes are clear, once the roads are clear, it's going to start sending the remaining bits of the frame out on the network. All right, let's talk about the client-server model here, and also the peer-to-peer. The client-server model depends entirely on devices called servers, and servers are computers dedicated to providing specific types of services or data, right? So email, maybe you have a web server too. We'll detail different types of servers in just a second. Anyway, a client like your computer or like your cell phone is going to use special software to ask a server for data or those services. It's going to say, hey, can you please send me an HTML file? I would really enjoy that. And what happens then is the server provides the data or service to the client. And so this is really commonly used. You're probably using it right now, maybe to watch this video. Crazy, right? Let's talk about different types of servers, speaking of watching videos. You got file servers, print servers, database servers, network controllers. They control accounts that are on a domain. So like if you have, if you're working for a school district or if you happen to be working for a company like Microsoft, there's a domain that you probably have an email address for. That means you have a user account, and network controllers are used to manage that data, that information. Also messaging servers, web servers, which are used to access HTML documents, and then also something called CTI-based servers. That's for telephone and computer systems, right? So if you have voice over IP, you're going to be probably using a CTI-based server. Couple of different operating systems here too. Like if you have a client, your client operating systems are going to be different from the types of operating systems that are used by servers. Just note the different tables there, or sorry, note the table there and the different operating systems that are used by a client and then by a server. These operating systems provide slightly different functionality, and so they serve different purposes, clearly, because clients and servers also do. All right, so a peer-to-peer model is different because it doesn't have a server. Peers are just client computers, and they all have equal capabilities and responsibilities. So each has the ability to send and receive data, or to serve and request data. And you know, it's also fairly common. We have Skype and voice over IP, like I just mentioned, and also cloud computing use the P2P model. You also may find file sharing networks like Napster, if you're old enough to remember that. I think Napster is still around, but in a very different form. You have Gnutella and then also G2. So peer-to-peer model is a little different. Each computer accesses data and requests data from its peers and not from a server. So those are two different models that you'll see in your journey through networking. All right, so just a quick recap here. 1.5, understand network topologies and access methods. We talked about different network topologies. We talked about the CSMA CD Ethernet standard and just the Ethernet standard in general. And we also talked about peer-to-peer and client-server models. So thank you so much for joining me for this module. I really look forward to seeing you next in Module 3. Hi, I'm Cullen, and welcome back to Networking Fundamentals. We're about to start with Module 3, Defining Networks with the OSI Model. Do a quick overview of our agenda here. We're going to cover two different objectives today. Objective 3.1, understand the OSI model. Talk about the different layers in this reference model, specifically the communications subnetwork, and then also its upper layers as well. We're splitting it into two halves. We're going to also review the TCP/IP model later in our presentation. Okay, so don't hold it against me that we're not going to go directly to that. But we will move on to 2.1, which also requires us to understand switches, right? Layer 2 switching and layer 3 switching. All of this layer discussion will make a lot more sense after we review the layers of the OSI model. And that's why we're going to review these two objectives together. All right, so without further ado, let's talk about the layers of the OSI model. Standards are sets of rules that ensure hardware and software released from different companies work together. They are the backbone of the internet, not the actual backbone of the internet, because there is something that helps us send data at super fast speeds called the backbone, but they provide the infrastructure really in which we're able to develop software and hardware that works together. There are a few different organizations that coordinate these standards. You may have already heard of me reference a couple. We have the International Electrical and Electronics Engineers. They focus on electrical and electronics fields. You have the International Organization for Standardization, which is called ISO. That's not actually an acronym. That's actually their name is ISO. So keep that in mind. It's not a spelling error on my behalf. I strongly recommend that you take some time to go ahead and Bing each of these organizations and learn what they do, okay? So you're commonly going to hear standards referenced in the same breath as protocols, okay? Protocols and standards, a little bit different. A protocol is a clearly defined rule and procedure that allows different manufacturers to create hardware and software that work together at a specific layer, right? So what are layers? Well, layers make up the OSI model. The OSI model is just a means of simplifying the complicated processes that occur during networking. So we talked about how data was transferred in a previous module. And this model allows us to follow along with that process and understand which protocols belong at which layer and sort of figure out what's going on, right? What's also cool about the OSI model is that if we design any kind of software or hardware, we can pick and choose which protocols we want to utilize in order to accomplish specific tasks. And because it may be, it doesn't matter. Let me rephrase. The protocols that we choose have no impact on the other layers, right? So if we go back to the slide here and you take a quick look, and let's say that I'm designing something for the presentation layer, the protocols that I use on the presentation layer have no effect on layer 5 or layer 7 or anything else. It's completely modular. So I can trust that layer 5, 4, 3, 2, and 1 are all going to do their intended jobs. Really, really cool stuff, and I wish we had more time to detail it. It can definitely be its own course. So let's talk about how the layers function. So if we're at this computer right here, when we send data to this computer over here, it doesn't just happen auto-magically, right? It's going to start by being created in an application, and it's going to walk down through each of these layers and then go all the way across in a bit format, right, in binary, zeros and ones, and it's going to come back up through that same process once it reaches its destination. It's just really cool to learn how this stuff works. And at each layer, there's a different type of protocol data unit, right? So, or a PDU. So you've got data is just called data at the application, presentation, and session layers. And then at the transport layer, data is broken into segments, which you've heard me reference previously. At the network layer, that segment turns into a packet because additional information is added. And then ultimately at the data link layer, the packet becomes a frame. And then at the physical layer, that frame is translated into bits and then transferred across the network. All right, let's go back to the presentation. Let's talk about the first 3 layers, the communications subnetwork. The communications subnetwork is made up of the physical layer, the data link layer, and also the network layer. So this is the bottom. It's the seedy underworld that makes up the internet, if you will. Layer 1, the physical layer, it just defines the electrical medium for data transfer, right? So not necessarily an electrical medium, but a physical medium, right? Physical layer components, you've got cables, jacks, patch panels, punch blocks, hubs, MAUs. Some of these things you might be like, I have no idea what this guy's talking about, and that's okay. Go ahead and take a quick second to bing them. Just for the sake of time, we don't have enough to cover every little tiny detail. So keep that in mind if you hear me say something that doesn't make a lot of sense. Just take some initiative and bing it. You'll be happier for it, okay? Physical layer concepts, we've talked about topologies. We talked about serial data transfer. We're going to touch on baseband versus broadband, and we will talk about analog and digital encoding here in a while too. Once again, the unit of measurement here at the physical layer is bits. Bits, as they move up, different slide. Ethernet standards. We just talked about these really quickly here. Ethernet standards, it's a local area network standard, like we mentioned in our previous modules. Defines a communication method for high-speed data exchange among devices. And you're commonly going to see that, if we look back at the presentation here, you're commonly going to see that the technologies here are referenced in this particular format. 100 base T as an example. 100 is for 100 megabytes per second. If it was in gigabytes, it would be 100 with a capital G, right? Base is short for baseband, which is a technology that we can detail a little bit later. And then T stands for twisted pair cabling. So we know that the medium that's being used is just copper wire. Okay. Keep that in mind. All right. So now going back to talking about bits, as bits move up the stack to layer 2, from layer 1 to layer 2, they're going to be turned into frame, or rather, they're going to become frames. The data link layer is going to establish, maintain, and decide how transfer is accomplished over a physical layer. So it's going to prepare your data for transmission on that physical layer. Data link layer components are your network interface cards, bridges, which are technology that we'll talk about a little bit later as well. And the unit of measurement here is frames. The data link layer is responsible for making sure that data is transferred properly and that there aren't any errors in it that occurred during transmission, right? So that when the computer on the other side or the device on the other side receives that data, that it is whole and prepared to be turned into the beautiful files that we see on screen. All right. Something that's really, really important here at the data link layer, and we talked about this as a physical address earlier, is MAC addresses. MAC is short for Media Access Control, and every single network adapter on an Ethernet network has a MAC address. A MAC address is very, very similar to your fingerprint, right? They're unique identifiers. So this is my finger, right? All of us have fingerprints, and they identify us as unique individuals. Network cards, very similar in that regard. They have MAC addresses, which identify them as unique devices. Okay? A MAC address, so we take a look back at the screen here, it is 6 octets in length, written in hexadecimal format. And so you might be like, what does that mean? Hexadecimal, it includes 0 through 9, and then A through F. So you have 16 different characters there if you include 0 through 9 and A through F. And notice here, there are just 6 octets. Each pair of hexadecimal characters represents a byte, right? So that's 8 bits. But this first portion of a MAC address typically references the manufacturer, right? And then the second portion is going to be unique to the device. So, cool bit of information. And remember that sometimes we'll call MAC addresses physical addresses as well. All right, so now that we've talked about the first 2 layers, let's talk about layer 2 switching. So how do the devices that operate on networks, how do they function within these 2 layers? So first off, let's start by talking about what a switch is. Okay, a switch is a central connecting device, like we had detailed earlier. Switches use MAC addresses to establish point-to-point connections, and what this means is that we make sure that if we have device A and it wants to send data to device B, it can send it directly to that device, right? It doesn't have to broadcast all that information to all other devices that happen to be connected to a switch. If you take a look at this switch example down here, you see a lot of different ports, right? So there are a lot of devices that can connect to a switch. It's really important for security's sake that if you want to establish point-to-point communication, that you actually are able to do that, and switches allow you to do so, okay? Hosts, of course, they connect to switches by plugging Ethernet cables, or rather you can connect a host to a switch by plugging an Ethernet cable into the host and to a switch port. Okay. Another cool thing to note is that every single port on a switch has its own, or it's associated with its own specific MAC address, right? So the device that's connected to it, that port on a switch is associated with the MAC address of the device that's connected to it. Okay. All right, so we talked about what a switch is, but what's a layer 2 switch specifically? A layer 2 switch, just the most common type of switch that's used in a local area network. And like I mentioned previously, they direct frames on a LAN based on physical addresses or MAC addresses. Each port of a switch is mapped to a MAC address of the device that's connected. So a little bit redundant there, but pretty good information, right? So you might have 2 computers. Maybe we have a laptop down here that features that MAC address of 23, 5C, F7, and so on. This port right here is then going to be dedicated to that MAC address. So these guys function, layer 2 switches, they function just simply using the MAC address to dictate where information is going to go. So if I have this example here, actually, let me back up just a touch. Let's say that this computer here wants to send information directly here. And we'll go ahead and make it so that this laptop down at the bottom is directly connected to a port that's associated with this laptop's MAC address. And so that's how information is going to end up at its proper location. The switch just uses that MAC address information to direct the data to its destination. Oh, I knew that something was funny, and here you have MAC addresses that just popped up. My apologies. I didn't realize that those were going to transition, guys. We had talked about virtual LANs as well, and I just want to briefly touch on this. Layer 2 switches, they allow for virtual LAN implementation, okay? And there's a standard here that's involved to support VLANs, it's 802.1q. I've highlighted it so that you know that you should go and do a quick Bing search in order to learn a little bit more about that. But as I mentioned in a previous module, what happens is that as data frames are sent, tags are added so that they're only directed to computers on their specific VLAN. All right, let's keep on checking. So you might be wondering, like, how do these switches remember MAC addresses? Well, switches have memory that's dedicated to remembering these addresses. Switches are just going to map the MAC addresses of connected computers to their ports in something called a content addressable memory table. All right, so you can see, I guess a basic example here. It's not a table as we think of it, right? Because it's really simplified data. But a sample CAM table is there. And note that if you have port 1, you're going to see that this MAC address right there is associated with it, and so on. Okay. The memory of a CAM table, though, know that that memory is limited. And so there's communication that occurs between a laptop or a PC and the switch that it happens to be connected to, where you actually send that MAC, each device is going to send its MAC address onto a switch. People can take advantage of the fact that switches store MAC addresses in their memory by constantly sending MAC addresses and flooding that switch and making it difficult for it to be able to store that information. And then that can render the switch inoperable. So keep that in mind. All right, so layer 3 switching is a little bit different, okay? Layer 3 is the network layer. Right? It controls the operations of routing and switching. It translates logical addresses or names to physical addresses or vice versa. So if you're receiving data, you're going to go from a physical address into a logical address. A major protocol that we're going to learn a lot about today, called the Internet Protocol, is a network layer protocol. Also IP is typically what it's referred to as. And devices that work at the network layer are routers, and then layer 3 switches, which can also be called IP switches. Okay. There are a few different network layer components. You got IP addresses and also subnets, which we featured in our last module. And the unit of measurement here is called a packet. Layer 3 switches are different from layer 2 switches because they direct data using IP addresses instead of MAC addresses, okay? So they forward packets instead of frames. They can perform all the same functions as routers, but they're not routers, okay? The benefit here in using a layer 3 switch versus a router is that they can actually forward packets faster than routers. And detailing how this is done is a little bit beyond the scope of this course. But if you're interested, once again, take that initiative and go ahead and Bing it, right? All right. Let's go ahead and move on to the upper OSI layers. Layer 4 is a transport layer. This is my favorite layer. I don't know why, but I always geek out whenever I get a chance to teach this layer in class. The transport layer ensures that the messages are delivered error-free, in sequence, and with no loss. And I think that that's such a cool thing, okay? There are a few different protocols that work at this layer. They segment messages, right? Those protocols. They ensure correct reassembly, like we mentioned previously, and they also do something called message acknowledgement. This is sort of like a certified mail. So like if you send grandma a box of chocolates and you really want to make sure that she gets those, she's got to sign for them upon delivery, and that's what message acknowledgement is. We'll detail that here in a second. And it's also responsible for message traffic control. Within the transport layer, there are both connection-oriented and connection-less protocols. And we'll detail those here in just a moment. The unit of measurement used, segments or messages. All right, so let's take a look at the screen here. Take a look at the PowerPoint presentation. Connection-oriented communications. They require that both devices involved in communication establish a logical connection. So it's like, hello, I'm a PC. Hello, I'm a server. All right, so they establish communication. This is considered sort of I guess you would call it a reliable network service, because if you have established communication, if you're doing this in person with two people, you would know the other person, you would know who they are, and all of a sudden they become more reliable. And so what's going to happen is that if I'm the PC and you're the server, I'm going to say to you, I'm going to send you something important, and you're going to acknowledge that and say, okay, I'll let you know when I get it, right? So if that important item or that important data is sent by a PC to a server and it doesn't reach the server, then all of a sudden the server says, hey, resend that data. And of course the PC will. All right, so let's talk about connectionless communications. End-to-end connection, not necessary at all. Every packet that's sent has a destination address in the header. And really all that happens with connectionless communication is that packets are just sent like one after the other. There's no guarantee that they'll reach their destination, and no guarantee that you know to resend them or that your device knows to resend them if they don't reach their destination. So a little bit different example where a PC is saying, I'm sending something, and of course you've got a server over here that's just sleeping at the wheel. So we're going to send packets in a stream, and there's absolutely no guarantee that they have been received. So connection-based protocols, we've got two that we can detail. Actually, there's one connection-based and then one that's connection-less. The connection-based protocol is TCP, or the Transmission Control Protocol. It's a reliable byte stream service. You're going to see this being used and leveraged by, maybe email applications, other protocols like FTP, where you need to download an entire file guaranteed. In contrast to UDP, it's connection-less, it's unreliable. You're probably going to see this if you're streaming a movie or streaming some kind of audio. Of course, these technologies, there are a couple different variants. And so if you're really curious if YouTube or if Spotify or something along those lines, which protocol they're using, go ahead and take some time to look it up. That's a really interesting way to learn about these transport layer protocols. All right, so like I mentioned there, if you're web browsing, you're probably going to be using TCP. If you're streaming media, probably going to be using UDP. TCP, it's only used for one-to-one communication, right? And UDP can often be used for one-to-many communication. So for broadcast or multicast. Broadcast, of course, we covered that. It's when maybe your device wants to send a communication to all of the devices that are on its local area network, and then multicast is if you would send it to just a few select devices on a local area network. All right. Another construct of the TCP layer or layer 4, the transport layer, is ports. Okay. Ports are used for sending and receiving data transmission, right? It's all that ports are is they're like little doorways that are dedicated to specific programs or specific types of data and protocols. There are a total of 65,536 ports. They're all numbered between 0 and 65,535. That's a lot of ports to remember. All of these guys are defined by IANA, the Internet Assigned Numbers Authority, and I can't imagine having to memorize all those different ports. So thank goodness there's somebody out there who's willing to handle it for us. That being said, there are some common port numbers that you want to make sure you remember. These are definitely going to be tested on the exam. These are extremely, extremely common. So do you know FTP, SSH, Telnet, SMTP, DNS? DNS stands for Domain Name System. We'll detail that later. HTTP stands for Hypertext Transfer Protocol. It's in your URL bar in your browser probably right now, or some variant of it is. Just make sure that you take time to really understand these port numbers and do a little bit of research on each of the ones that are listed here, each of the associated protocols that are listed here with those port numbers. All right, so moving on from layer 4, we get to layer 5, which is the session layer. This just manages session establishment. So if you start using an application online, that's a session right there. Right? You log in with your username and password, and you start a session. And when you close out of that application, you end a session. And so this layer is responsible for controlling just the name and address database for the OS. And to do that, we've got a protocol called NetBIOS. It works at this layer. Definitely go ahead and give NetBIOS a quick Bing search and learn a little bit more information about it. All right. Layer 6 is the presentation layer. The presentation layer is responsible for taking data from the sender and then translating it into a format that your operating system can use. So if you're using Windows 8 and about to be using Windows 10, the presentation layer is going to be responsible for helping to prepare the data for rendering on screen. Okay. Here it's also, if you're sending data, it can be responsible for data compression, data encryption. So it's definitely responsible for components of security in terms of data transfer. And there are also something called redirectors that work on this layer. And redirectors, they allow you to, I'm trying to think of the best way to explain it. And here I have it listed as mapped network drives that enable a computer to access file shares on a remote computer. And I guess what I'm getting at is that if you're working for a business or for a school district, you might store your files remotely, and a redirector would be put to use there so that you can access a remote drive through a remote protocol. Okay, we'll detail a couple of those a little bit later. So. All right. Layer 7 is the application layer. This serves as a window for users and application processes to access network services, and this is really where message creation begins. It's really important to note that this layer is not the application itself or any application itself, but this layer represents the protocols that are used or initiated by this layer. Okay, a few of them are FTP, SMTP, Telnet, and also RAS. All right, so just a quick review of the OSI model here. You've got 7 layers. There are some of the key protocols that are featured at each of the layers, and also the different types of devices that are used at each layer. All right, so there's another reference model that we use. It's called the TCP/IP model. It's very similar to the OSI model, but it's composed of only 4 layers. So you've got the application layer, the transport layer, the internet layer, and also the network interface layer. I remember the order of this as a tin. I think of it a tin cup, and I'll try my best to draw one here, right? So if you ever have like a soup can or something like that, this is how I think of it. I think of it in 4 layers. This is kind of silly, so I apologize if my animation's getting in front of the words. But I think of a tin cup with 4 different layers, right? And that, for whatever reason, just helps me remember the order of the TCP/IP model layers. Okay. Notice some of the same protocols are listed there, and we'll see in just a second that the TCP/IP model definitely matches up and aligns with the OSI model. The only difference here really is that there are 4 layers instead of 7. And here's how that matchup occurs. So note that in the OSI model, the application layer, the presentation layer, and the session layer, they match up with the application layer in the TCP/IP model. Transport layer, only one that remains the same. The network layer is actually called the internet layer with the TCP/IP model, and then the network access layer is actually referencing the data link layer. The physical layer is entirely skipped altogether in the TCP/IP model. All right, so that's it, ladies and gentlemen. Just a quick recap. We talked about Objective 3.1, understand the OSI models, featuring the layers of the OSI model, more specifically the communications subnetwork, and then the upper OSI layers as well. So we covered layers 1 through 7. And then we had Objective 2.1, understand switches, and we talked about layer 2 switching and layer 3 switching, and the difference between both of those devices, a layer 2 switch and a layer 3 switch. Thank you so much for joining me for this module. I really look forward to the next one. I'll see you again in Module 4. Hi, I'm Cullen, and welcome back to Module 4 of Networking Fundamentals. Let's go ahead and check out our agenda and get started here. Just a couple of quick things to go over in this module. We're going to focus on Objective 2.3, understanding media types. We're going to talk about twisted pair cables and also fiber optic cables. So the cables that connect devices all around the globe and that help make up the internet. All right, so wired networks. They're really important. And as wireless connections, like as easily accessible and as widely used as they are, we still depend on wired networks to send our data. Because even if we're using our phone, that phone's connecting to a wireless access point, and that wireless access point is probably connected by a wire to a switch. The most common type of wire used throughout networking is made of copper. It's called a twisted pair cable. And the cable that we rely to send our data super long distances at ultra fast speed is made of glass fiber. And that fiber transmits data via light. And we'll touch on that a little bit more here in just a few moments. But first, let's focus on twisted pair cables. So twisted pair cables, once again, they're very commonly found, the most common, in fact. And the reason being is that they're cheap. They're pretty fast, and they're really efficient at sending data via electrical pulses. We got multiple types of twisted pair cables are available, and they can be installed temporarily or permanently. So if you take a look here down on the bottom right of the screen, we have a patch panel there, right? You have a port being terminated up here in the top right screen. Those are 2 permanent installations of twisted pair cables. And here you have something called a patch cable, which we typically refer to as an Ethernet cable. All right, part 2 of our twisted pair journey. Each twisted pair cable has 8 wires, and those wires are grouped into 4 pairs. Notice here we have a brown pair, we have a green pair, a blue pair, and then an orange pair. Notice that within each pair you have one that's solid, and then you also have one that is, I guess you would call it striped, right? It's white with an orange stripe in this case for this specific example, but that's the case for every single pair. Each pair is twisted, that's where the twisted and twisted pair comes from, in order to reduce something called crosstalk and interference. We'll detail what crosstalk and interference are in a little bit, okay? So don't worry about that right now. But then we surround all those twisted pair cables with a plastic jacket. That's typically what gives it that quintessential blue look that you see on a standard Ethernet cable. Okay. All right, so patch cables. These are the cables that we use to connect one device to another, or one device to an RJ45 port. Each end of a patch cable is terminated with an RJ45 plug using a cabling standard. Okay, we're going to detail these cabling standards in just a moment as well. There are two different types of patch cables that we're going to briefly talk about, and they're called straight through cable and also a crossover cable. All right, so these cabling standards that we're about to touch on, they're developed by TIA-EIA, right? The Telecommunications Industry Association and the Electronics Industries Alliance. When making a patch cable, the twisted pair cables are placed in order, and that's part of the standard, right? The order is defined. We then use this device right here to do something called crimping. That's a crimper, by the way, in order to secure our wires into an RJ45 connector. Okay. Note here that that's placed down, trying to secure the cables into the connector. All right, so let's detail some of these cabling standards. You've got an older version, BOGB. Then we have the two that are most commonly used. We have 568A and then 568B. Notice here we've got got two models up on the screen for you. 568A follows a very specific pattern where you have the white and green, then white and orange, then solid blue, then white and blue, and then solid orange, and then the white and brown, and then brown. And then B is a little bit different here, okay? What you're gonna see is that the blue cables are in the same position, and then the brown cables are in the same position, right? So the blue occupy pin, sorry, I actually should probably just go ahead and show you over here on the chart here. The blue occupy 4 and 5, and the brown always occupy 7 and 8. The only thing that's different here is that the orange and green are swapped between a 568A and a 568B. All right, so we use straight through cables to connect PCs or the devices that we use every day to central connecting devices. The straight through cable, it's the most common type of patch cable, and it's called straight through because we use the same standard, right? The wires on each end are organized using 568B, both ends are, or they would both be organized using 568A. In contrast, a crossover cable is called a crossover because of the fact that if you start one end with the 568A standard, it crosses over on the other end to the 568B standard. So let's say that this PC1 here, and we have PC2. Let's say that this Ethernet cable is terminated with the 568A standard, and then PC2 is connected, it is terminated with the B standard. Okay, we would use crossover cables to connect two like devices, like a computer to a computer. All right, so let's go ahead and move on back to the slideshow. Limitations of twisted pair cabling. As we mentioned before, there may be some interference with twisted pair cables, and so they actually can only run about 100 meters, which is just a little over 300 feet, before they start suffering from something called attenuation. And attenuation is just simply the difference between the amount of information that's being transmitted and the amount of information that actually reaches its destination. Okay. And so what attenuation is basically you're saying signal loss, right? So we're losing data due to attenuation. Twisted pair cabling, also susceptible to interference, like I just mentioned. And note that there are 4 different categories of twisted pair cables too. Probably should have isolated these on their own slide, but my apologies. You can definitely download these slides and do that on your own. Note though that category 3 came before 5, 5 before 5E, and then 5E before 6, right? So notice how the maximum speed rates, the data transfer rates or bit rates, are increasing with each new category. Okay. All right, so we just talked about interference a little bit ago, and what is interference? All that it is just anything that can disrupt or modify a signal, and that ultimately would result in the corruption of data. There are a couple different types of interference. You have electromagnetic interference, you have radio frequency interference, and then crosstalk. Whoops. Electromagnetic interference can be given off by a microwave or anything that transmits an electromagnetic field. And what that can do is it can essentially just throw off those electrical signals that are being transmitted along a wire. Similarly, with radio frequency interference, radio frequencies can interfere with wireless communications. And so it may not impact the use of twisted pair cabling as much as EMI would, but it's definitely something that you should be aware of. And finally, you have crosstalk. And crosstalk actually occurs within an Ethernet cable. And so if you're sending data on one twisted pair and receiving data on another twisted pair, there may be some crosstalk that occurs where the electrical signals on one copper cable start to get mixed with the electrical signals on another one. And so that's crosstalk, and it can definitely lead to data corruption and attenuation. So, all right, let's keep on moving. To combat crosstalk, we actually can shield the twisted pair cables. And so not just crosstalk, but also just general interference can be addressed through the use of shielded twisted pair, or STP cables. All that we do is we wrap each pair with an aluminum shield, and then we put all of our pairs back inside of a plastic jacket. Keep in mind, shielded twisted pair, typically a little bit more expensive than unshielded twisted pair. We also have a certain type of cable that's called plenum rated, and these types of cables are installed inside of walls or above drop ceilings like you might find in a school, where they can't be hurt by sprinkler systems or any other cabling that, or I guess any other systems that you might have, like lighting systems, things of that nature, electrical systems. And so plenum rated cabling is important because if there's a fire, these cables have a Teflon coating that makes them, that protects them, right? They don't give off high amounts of smoke, okay? They're used in these situations because standard twisted pair cables have a PVC jacket, which can actually emit a really deadly gas, which makes it really, really dangerous in a fire situation. So you definitely would want to use plenum rated for anything that happens to be near electrical work, happens to be hidden away in the ceilings, or embedded within a building's infrastructure, because you certainly wouldn't want to cause any more hazards than might have already occurred if there was a fire. So keep that in mind. All right, fiber optic cables, right? The last part of our cabling journey here. Fiber optic cables transmit data using light instead of electricity. We commonly just call them fiber. They're actually made of glass or plastic, right? That's what makes the fibers, is glass or plastic. They have incredibly higher data transfer rates, and they're used when in a situation when high data transfer rates are required, and also when data needs to be transferred longer distances. And that's because data can travel at the speed of light, which is really fast. You've probably heard that, the speed of light. Also, longer distances. Light can travel a much longer distance than electricity can before the signal degrades. And so that's why it works so well. It also happens to be a little bit or a lot more expensive in some instances. All right, so there are a couple different modes with fiber optic cabling, and this can be a little confusing, so do make sure that you're paying close attention right now. There's single mode, and it actually just carries data through a single ray of light, and light in this instance is created by a laser. It's used for much, much longer distances, like 10 kilometers up to 80 kilometers, which is really, really far. This is the type of fiber optic cabling that's used to send data across oceans, right? Just mind-boggling. Multimode is a larger fiber, so there's a larger fiber density, and that actually carries multiple rays of light. And the way that this happens is that LEDs are used in order to beam light at different angles in order to transfer the speed. So I can't really do it with my two fingers here, so I apologize. But what happens is the light bounces off of one side of the fiber up to the next, and it never actually hits the different light beams. They just go ahead and they intersect, and they're typically different colors of light as well. And this allows you to send multiple data streams on the same fiber. Super interesting as far as I'm concerned. But another quick thing, if you want to point back to the screen here, is that we use multimode fiber for shorter runs, right? So it's just 600 meters, which is still a lot longer than any of your typical twisted pair cables, but it's something to be well aware of. Note that there are multiple fiber optic connector types. This isn't necessarily something that you're going to be tested on, but I honestly would strongly recommend that you go ahead and do a quick Bing search and take a look at the images for each of these connector types. Very fascinating stuff, how you build fiber optic cables. Finally, we do have a ton of different fiber optic cabling standards that are available. Definitely want to go ahead and take some time to review this chart. You don't need to memorize it, but do look for trends, okay? Definitely take time to look for trends. Make sure that you know and understand simple things like the specific cabling standard you want to use for the longest transfer distance, and also be aware of I guess what you would say the fastest transfer rate too. Look for things like that, and also look for the slower ones too. All right, so thanks so much for joining me, ladies and gentlemen. We'll do a quick recap here of Objective 2.3. We talked about twisted pair cablings, unshielded twisted pair and shielded twisted pair. We also touched on plenum rated cables as well. And then we just briefly glossed over fiber optic cabling and a couple of different fascinating aspects about it and how it's able to send data really far speeds at really fast rates. Thanks so much for joining me. I look forward to seeing you in the next module. Bye. Hi, I'm Cullen. Welcome back to Networking Fundamentals. We're going to get started right now with Module 5 and continue our journey through understanding wired and wireless networks. Let's go ahead and get started. Let's take a look at the agenda on screen here. Like I said, we're going to cover Objective 1.4, understand wireless networking. And so that means that we've got to understand wireless devices and wireless standards. All right, so let's talk about wireless networks. For a wireless network to work, all devices have to be connected through a wireless network adapter. And so it's a little bit different from the wired one that you guys saw a picture of earlier in one of our modules. I think it might have been Module 2. I can't recall. Don't hold it against me. And so those devices, they connect through radio signals to a wireless access point. That wireless access point, of course, is an essential connecting device that's capable of sending and receiving data with radio signals as well. And those access points still use Ethernet cables, right? They're connected to the internet, for instance, by Ethernet cables, copper cabling still. Okay. So let's talk a little bit more about wireless network adapters. They enable connectivity between any device and a wireless access point, and they work simply by translating bits into radio signals. And if you actually just take a look at my hands here, all that happens is that radio signals they modulate, so they sort of go up and down, and that's how they represent zeros and ones. A little different from the way that you represent zeros and ones in binary data with electricity or with light. So anyway, back to the screen. Wireless network adapters, they take a lot of different forms. Most laptops now have internal adapter cards, but there are still, and onboard wireless adapters too, which means that it just goes on your motherboard or your MOBO, as tech geeks might call it. But there are still external adapter cards and also USB adapters that allow you to connect wirelessly. Wireless access points, they can come in many forms as well. Oftentimes they're located in our home routers, our SOHO routers at our home office or small office. And, you know, wireless access points, like I had mentioned previously, I hate to hammer this down, but they're connected to switches. Right, and we do have dedicated ones that are specifically for the purpose of sending and receiving data in large organizations. They might be hiding in a ceiling somewhere above you right now, depending on where you're watching this video. But wireless access points, they simply do that same thing. They translate bits into radio signals, and then they send or receive it. And they do a good job of receiving them and then translating them into the electrical signals that are required to transmit data to a switch or to a router. Another technology that we haven't talked about is a wireless repeater. Wireless networks are limited in how far a wireless signal can transmit. So if you think about the range of your wireless access point, it only goes so far. You could actually place a wireless repeater here at the end of a network in order to extend the signal range of a wireless access point. Repeaters do this by reading the signal coming from the wireless access point, and then they go ahead and they repeat it and send it out. And of course, we got to make sure our data finds the device there, right? And similarly, it just reverses that process in order to make sure that your device, if connecting to a repeater, is able to send data back onto the local area network and onto the internet, hopefully, right? We'll detail a little bit more about what the internet actually is a little bit later too. Next, bridges. Bridges function a very similar way to repeaters. Bridges sit in between two different wireless local area networks though. And what they do, just like bridges in real life that connect two different sides of a ridge or maybe a gully or something along those lines, is they bridge those two networks together and connect them together. This is known as bridge mode. Okay, it's I sort of find it funny every time that I use these semantic words, because sometimes there's just not a better way to describe it than saying like, oh, it bridges things. And as a teacher, I feel like I should get on my own case about using a word to define itself, but this is definitely what it does in this instance. All right, so let's talk about wireless standards. For wireless networks to function, all of the devices, all of the wireless adapters have to use the same wireless networking standards. There are a number of different networking standards that define wireless communications. They're commonly referenced as Wi-Fi. Right? Those are the standards, the body of standards that dictate the data transfer rate, connection frequency, and more of wireless communications. The standard, however, is commonly referred to as 802.11, right? So let's take a look at this chart over here on the right. This is something that's almost, I've taken this exam a couple different times, and I've seen content from this particular chart multiple times. It's really important. A little odd fact, just so you know, is 802.11b was the first wireless standard created. It was the first to market, rather. Shortly after followed A. And what I want you guys to notice is that these two are the key to really understanding this whole table. B came first, so its data rate was what I say slow, and its frequency was low. Okay. A came along, and it was fast, and its frequency was high. I sort of think about the way that alleles in biology work, and I think about the fact that when you create a new technology, it sort of inherits different features from previous technologies. And so I like to think of G as sort of being a child of A and B. And so if we go back to the screen here, you'll see I always think of G as inheriting 54 megabytes per second, or not megabytes, megabits per second from A, whereas it inherits 2.4 from B. So while B is slow and low, A is fast and high, and so G is fast and low. And so if A and B were parents, right, they would pass along those traits to G. And of course, that same type of analogy doesn't necessarily work that well with N down here, but N just gets way faster with 600 megabits per second. And then of course, it uses both frequencies. It uses 5 gigahertz or 2.4 gigahertz as a frequency. So I don't know, hopefully that little analogy helped you remember the difference between those standards. Definitely something that you're gonna see on an exam. Okay. All right, 802.11n. This is the standard that's commonly used right now. There's actually one that's newer than that. I believe it's 802.11ac. But it's a standard because it's fast, right? And there are also a couple of other factors too. It supports multiple antennas. So if you have a wireless router at home, simultaneous connections and data streams can flow into that wireless router. There's also something called frame aggregation that it supports, which is just sending 2 or more frames in one transmission, so the same radio signals, which can double your bit rate. There's also something called channel bonding. So channels we're not going to detail here. It's a little bit beyond the scope of this course, if I recall correctly, or rather beyond the scope of the exam. But you don't want your channels sitting right next to each other because that can cause some problems when you transfer data. But if you're using 2 channels in combination with each other, then you're able to send twice as much data as possible, and it's really quite a positive thing for wireless communication. All right, so let's talk about wireless network topologies. So similar to wired networks, there are different ways to connect devices in wireless LANs. Recall that these arrangements are called physical topologies, but know that when you're connecting wirelessly, the physical location of your devices don't necessarily always matter as much as they do when you're using physical cables, right? So there are 2 common ways, though, to connect devices wirelessly. There's ad hoc mode and also infrastructure mode. Ad hoc mode is used by, or rather, I should say that devices are organized in something similar to a mesh topology. So if you recall from when we were talking about the mesh topology, notice that every single device is connected to every other device in the topology, right? And of course, those red lightning bolts, they resemble wireless communication. Clients they communicate directly with each other. And so this is an example of a peer-to-peer network like we had talked about previously. Ad hoc mode is used less commonly than our next mode that we're going to feature, which is infrastructure mode. And this is probably the one that you're using right now, even in your house. Could also use it at work or even at school. Okay. Infrastructure mode, most common way to connect wirelessly. What happens is like we've been talking about this entire time, your device is going to connect to a wireless access point, which then is connected to a cable that trails off to a switch and off into a router. When clients want to connect, they use a service set identifier. So if you are connecting to the internet through an internet service provider and you have a home router, you probably are connecting by using a service set identifier, an SSID, right now. Mine at home, if I can divulge this, and I'll write it up on the screen for you, is Go Seahawks. And I'm able to locate my network because of that name, right? Before a device can access the network, clearly you have to try to connect using that name, but you also are going to authenticate with a password. That password is gonna basically prove to that wireless access point that you belong on the network. Oh, look at that. I already covered all this information. Make sure to read this really quickly, and we'll go ahead and move on. One thing I'll point out from this slide is that for security purposes, you can hide the SSID from people, right? They don't have to see it. Pretty cool. So one of the things that's not often talked about with wireless communication, at least in general conversations, is that though it's convenient, it's not always secure. And that's because the data is just traveling wirelessly through the air, right? The radio signals just travel unbeknownst to us. And that means that anybody can try to access that data, right? Like it's publicly actually available out there if you have the proper technologies. And so we have to protect our wireless communications. And we do that using wireless encryption protocols. The table to the right is going to detail a couple of different wireless encryption protocols for you. You may be familiar, you may be using some of these at home. But what happens with encryption is that we scramble data to make it unreadable to hackers. We do this using keys. And the size of your encryption key is going to dictate how strongly your encryption, or how strong your encryption is, right? So the longer the key, the harder it is for somebody to hack your data. So if you have a 256-bit key, it takes a lot longer for a computer to be able to try to hack your data and figure out what kind of messages you're sending back and forth. In contrast, a 64-bit key probably isn't going to be super secure now. All right. Lastly here, we're going to talk about 802.1x. It's a standard that's used to secure wireless communications. Just three basic components within this type of a setup, all right? And you'll be able to see all these components over here on the right-hand side in this graphic. First, you got a client computer called a supplicant. Then you have a wireless access point, which is called a network access server. And then you have a radius server, which is going to be responsible for authentication. What happens in 802.1x is that the supplicant is going to contact the wireless access point, and it requests access to the network. The wireless access point then contacts the radius server, right over here on your right, to see if the supplicant's username and password is in the database. If it is, and let's go ahead and switch to green so we can say that it is, then what happens is the computer now has access. It has the green light to utilize the network and its resources. And that very well mean that all of a sudden it can start sending data out onto the internet and receiving data from web servers across the internet. All right, so that's all we've got for this module. Hope you join us next time. We'll do a quick recap here. We just talked about wireless devices, wireless standards, and also how to secure wireless networks and the technologies that are involved there. So I hope you had as much fun as I did. Thanks again for your time, and I'll see you next module. Hi, I'm Cullen. Welcome back to Module 6 of Networking Fundamentals. We're going to get started here with understanding Internet Protocol, or IP, as everybody likes to call it. All right, let's go and take a quick look at our agenda. We're going to go ahead and cover two objectives today. First one, 3.2, understand IPv4. Within that, we're going to detail IP version 4 or IPv4. We're going to talk about the address categories for the protocol, talk about network address translation, then move on to discuss default gateways and DNS servers, and then finally touch on subnetting and CIDR. Then lastly, we'll go ahead and touch on IPv6 as well as a protocol, the ultimate replacement or the eventual replacement for IPv4. Okay. The Internet Protocol resides on the network layer. Go ahead and recall that from our detailing of the OSI model. IP addresses are used to help devices send and receive data across networks. Remember that they are very much like our mailing addresses. So if you mail something to your mom, or you mail something to a friend, same way computers communicate, they use addresses in order to make sure that information goes to its intended destination. IPv4 currently is the most commonly used communication protocol, but IPv6 is starting to replace it, and it's already being used more widely everywhere. Okay. All right, so let's talk a little bit more about IPv4. So this is the fourth version. That's why it says v4. It's the first version, though, of the IP protocol to be widely used. IP addresses consist of 4 octets. All right, so we have 4 octets, and we touched on this briefly in a previous presentation, but super important to know, okay? So you got 1, 2, 3, 4. We have 4 different examples here. Each has 4 octets. Each octet is separated by a decimal point. You may refer to it as a period, but call it a decimal for this sake. Each octet represents 1 byte, or 8 bits, meaning that an IPv4 address features 32 bits. So what that also means is that we can convert those decimal values into binary. So let's take a look at a simple octet here. Let's say 192 as an example, okay? We'll go back to this chart. If I take a look at the number 192 as an octet, and I say, hey, I want to convert this into binary. What I can do, if you take a look at this chart here, is if 128 as a value fits into 92, then I can go ahead and I can put a 1 here and say yes, I can in fact subtract 128 from 92. So if I do that, do some math, probably wishing I was using a calculator right now, aren't you? What we end up getting is 64. Well, so now my leftovers, 64. Can I subtract 64 from 64? The answer is yes, so I'm going to go ahead and I'm going to put a 1 right here. And if I do that, 64 minus 64, all of a sudden I have 0 left. You might be bummed out that you have 0 left, but it's okay because it actually makes the rest of our job very, very easy. I'm going to say, hey, can I fit 32? Or rather, can I subtract 32 from 0? Well, no, there's nothing there remaining, so all of a sudden I put 0. The answer is no, and that's what 0 represents, is no, or false. Same thing with 16. I've got a 0 there. There's nothing remaining, so I can't even subtract 8, or 4, or 2, or 1. And so, of course, my decimal equivalent for this would be 192. And if you take a look at the examples up above, say for 224, we did the same thing here as well. So you see, we can subtract 128 from 224, and then whatever's left over, we can subtract 64 from that. And then, of course, we would only have 32 left over if we did that, which means that we put a 1 here, and then the rest are all zeros. And that's how we would translate decimal into binary, and also vice versa, how we can take binary and translate it into decimal, okay? Great job. If that was a little hard to follow, I would definitely recommend that you go ahead and Bing decimal to binary conversion or IPv4 decimal to binary conversion. Really quick thing for you to do. There are a ton of really great tutorials out there. There are also some packets that you can find if you want to practice. Definitely helps out a lot. All right, so let's go on. Let's talk about IPv4 address categories. There are 5, and they've been categorized, or pardon me, they've been categorized into 5 different classes, right? The classification system, it's called classful addressing or classful network architecture. And in this system, the first octet of an IPv4 address defines which class the address belongs to. So if the first octet is in the range of 0 to 127, then it belongs to class A. If it's in the range of 128 to 191, then it's in class B, and so on and so on. So I'm going to show you a quick little trick for remembering these IP class ranges, okay? If you convert the first octet into binary, and the very first digit is a 0, then you know it's class A, because 0 means that you couldn't subtract 128 from it, right? And if you have 127, you can't subtract 128, can you? So now watch, because there's a little bit of a trend here, okay? And I don't want to spend too much time on this, but I think that this is really helpful, and I wish somebody would have taught this to me when I was learning. 128, we can subtract 128 from that. So there we go, right? But if we have 128, and then if we looked at that second digit, if there was a 1 there, that means that we would have 192. Well, the range only goes to 191. So what that means is that this second digit has to be 0. So just like we had the first digit for Class A addresses in the first octet had to be 0, the second one in Class B addresses has to be 0. Now, if you take a look at C, the third digit has to be 0. And that's because if that was a 1, then the lowest possible number that we could have within that range would be 224. So now we go on and we look at D, and you guys are like, man, this is no longer rocket science. This is pretty easy stuff. It's that fourth digit is 0, and then all of a sudden E is everything else where you start with that fifth digit as 0. But notice here that that last digit's 1, and that's because we reach the top of our range. And I don't know if I explicitly mentioned it. It should have been featured on one of the slides, but I will definitely tell you that octets, they have to fall in the range of 0 to 255, okay? Really important stuff to know. But hopefully that was helpful in terms of remembering how the classes are organized. It's a really challenging thing, so if you are having troubles with it, don't be too hard on yourself, okay? All right, so one thing about Class A is that there is a reserved network address for loopback IP addresses. And loopback IP addresses are used for testing and ensuring that that your network adapter is properly functioning. Every device is automatically assigned the 127.0.0.1 loopback IP address. A funny way to remember this is I have one of my friends who has it's supposed to be like Home Sweet Home, but it says Home Sweet 127.0.0.1. Just referring to the fact that that's the IP address, the loopback IP address that always points back to home. Okay, sort of geeky, but if you Google it or if you Bing it, it'll probably come up. All right, so IP addresses also have subnet masks, and we did talk about that a little bit earlier. And each IPv4 address has a network portion and then also a node portion. Just for reference sake, a node is another word for host, by the way. There are a lot of different vocabulary words that we use interchangeably. So if you get confused, once again, don't feel bad. Just make sure that you go ahead and take time to clarify. It's really important that we get these things and these concepts and ideas organized in our heads. All right, so with Class A addresses, the default subnet mask is 255.0.0.0. And so what that means is that if you have 255, that portion belongs to the network. In contrast, if you have zeros, then that portion belongs to the hosts, right? So that helps uniquely identify a host or a node. So similarly, if we take a look over here at our subnet masks for Class C addresses, the first 3 portions are dedicated to the network. So that information in an IPv4 address is used to determine which network or identify which network a host or a node belongs to. And then that last portion is to specifically identify that unique device. All right, so within these classes, there is a number of addresses that are a number of usable addresses that are available for computers, okay? If you take a look at the chart down at the bottom, we look at the total number of networks and then the total number of usable addresses. So we raise 2 to the 7th power because if we look at an octet, and I'm just going to draw all zeros here, so don't hold that against me. We have the first one is listed as 0 because 2 to the 0th power is 1, right? And then the next one is 1, which would place us at 2, and then the next one is 2, which gives us 4, Next one's 3, which gives us 8. Next one is 4, which gives us, whoops. Next one's 4, which is going to give us 16. And then we have 32, because it's 2 to the 5th power. 2 to the 6th power would give us 64. And then 2 to the 7th power gives us 128. And so if that happened to confuse you, I'm going to go back here just to show you real fast at our decimal to binary conversion slide. This is where I was getting those values from, right? So here we have the first digit, the second digit, third, fourth, fifth, the sixth, the seventh, and then the eighth. And that's the power. These are all the powers that we would raise to as we move along digits, right? So it's 2 to the 0th power because you have 2 options in binary, 0 or 1. And so you're raising it to the 0 power, and that's how you get the value of 1, and so on and so on. Once again, that could be really, really confusing if this is your first time looking at this stuff. So if you do need to pump the brakes and you go need to do a couple of searches in order to better understand this stuff, don't feel bad. So going back to what we were saying, the total number of available network addresses is 128 in a Class A network. The total number of usable host addresses, however, 16,777,214. There are actually 2 more addresses that are available, but they're not usable because the first address is reserved for the entire network. So that becomes the network address, right? It's used by the default gateway, which is a router that's going to serve as the gateway, no pun intended, to the internet for your local area network. And the last address is used for a broadcast address. That's used when a device wants to communicate with all devices on a network. So make sure you take time to go ahead and study this chart and prepare yourself to recall the total number of usable addresses, and always remember that it's the total number of addresses minus 2, because you're going to subtract the 1 for the network address, right, the default gateway, and then 1 for the broadcast address as well. Okay, all right, let's move on to the next slide. Next, we've got public and private IP addresses. IPv4 addresses are further classified as public or private. And public IP addresses are just the ones that are exposed to the internet that anybody can see. And then private ones are hidden from the internet and any other networks. And so you've got private ranges here in this table on the right. And so you'll see that commonly, I bet if you probably checked your IP address right now on your computer, it would come up as 192.168.0.0. For larger organizations, it's going to start with a 10. For medium-sized organizations, it'll probably start with 172.16 if you happen to be on a network, a local area network right now. My apologies. All right. Next, there are also static and dynamic IP addresses. So IP addresses can be assigned statically, which means that they're manually assigned to a host, and so they don't change. That's what static means that it doesn't change. Dynamic, in contrast, means that it does change. And so with these types of addresses, we automatically obtain them from a server, which is pretty darn cool. So, if you're moving from location to location, you're probably having IP addresses assigned to you automatically, and you may not even be aware of it. This is something that completely just, gave me a headache, made my head spin when I was first learning about this stuff. So, all right. There's another reserved range for, or another reserved network, right? It's in Class B. It's called Automatic Private IP Addressing, or APIPA, right? If a client can't get an IP address from something called a DHCP server, which is Dynamic Host Control Protocol server, and an IP address hasn't been configured statically, then it auto-assigns this number to itself on the network. So it'll have an address within the 169 range. This is useful because if your computer can't access the internet, or there's something wrong and you can't automatically obtain an IP address, then you're going to get you're going to self-assign an APIPA address, and then that'll allow you to communicate with all the other devices that are on your local network. All right. Network address translation. Let's go ahead and move on and talk about how public and private addresses really function and how they work out in the open, out in the wild, if you will, right? Network address translation is just simply the process of modifying IP addresses while in transit across a traffic routing device. So what happens here is that this, let's see here. So we might have computer 1 sends information to a switch. The switch goes ahead and sends it off to the router. And then what happens is that that packet might have the addressing information of 192.168.0.255. And what's going to happen is that there is, and this is my translation process here, right? That router is going to go to work and it's going to translate this address into this one. It actually knows exactly what that address is, so the process isn't as messy as that, but I just thought it'd be more fun if I scribble on the screen. And so everybody that's out on the internet, right, this cloud here, they're going to see this public-facing address. They're never going to see the private address that's being used by the computer on the local area network. And this is a really cool process because what it does is it makes it a little bit easier for us to use IPv4 addresses. I guess I should have said that IPv4 addresses are limited. We actually have more devices than available addresses with IPv4, which is a huge problem. And so this allows us to make better, more efficient, more effective use of them. So, all right. And of course, here's a little bit more information on NAT, right? Stuff I just said. It was developed to provide a temporary solution to the shortage of IPv4 addresses. So. Okay, so let's talk about default gateways and DNS servers. For a device to be able to access the internet, if you're on your computer right now, it has to have a default gateway, and you also probably will need a DNS server unless you are really good at remembering and recalling IP addresses. Default gateways provide default routes for TCP and IP hosts, right? Our computers, our devices, to use when communicating with hosts across the internet. So anytime you send a text message, this process, default gateway is probably being used. The first IP address of the device that a client computer will look for is actually the address that belongs to the default gateway. And so this network address that we were talking about, the first address in a network range or on a network, is going to be assigned to a router. All right, that router is and it does serve as the default gateway. So keep that in mind. Here's a little data going through the router and then, of course, onto the internet. It's pretty exciting stuff, this data transfer. Let's talk about the domain name system, okay? If, let's say we want to go to Bing, okay? So I'm on the laptop and I want to go to www.bing.com. Well, that server that's located over here on the top right, that has all of the good Bing HTML files and all the other code that we need in order to create the Bing.com web page on our screen. And so what we need, though, is we need something to take that name and translate it into an IP address so that we can access the Bing server, because it's not called Bing.com. The server actually has an IP address. And so let me actually erase the ink because I think my animation is going to cause me troubles and make me back up with what I just said here. But let's now pretend that that's not the Bing server, but it's actually a domain name system server, okay, a DNS server, right? And so what's going to happen is we're going to type in bing.com into our browser, and then that information is going to be relayed to the DNS server. And then what happens is that DNS server is going to send us back the IP address for Bing.com. That's the actual IP address for Bing. And if you type that into your browser right now, you actually should be able to access Bing without typing in the name. But what it's going to do, what that DNS server did, was it translated that name into an IP address that we can then use to access the web server where Bing is located. All right, so lastly in our voyage through subnetting through IPv4, we're going to talk about subnetting in CIDR. Subnetting is simply the act of dividing a network into smaller subnetworks. It's similar to taking a big old pizza and cutting it into slices, and the size of those slices differs based on the objective, right? You can make bigger or smaller slices. By default, all computers are like one big pizza. They're just one subnet or network with no divisions involved. So we have to make sure that we subnet them. That's where the term subnet comes from, by the way, in order to make sure that we efficiently use our IPv4 addresses. All right, so with classless interdomain routing, if we take a look here at our slide again, it's intended to replace classful IP addressing, and it has, because we once again want to slow the exhaustion of IPv4 addresses. We don't want to run out. We want all of our devices to be able to access the internet and communicate with each other. It's based on something called variable length subnet masking, and that allows us to divide a network into those different size subnets. To implement VLSM, what happens is networks borrow bits from the host portion of an address. So if you have 32 bits, like if we looked at a class A address, if you had 8 bits that were for a host, 8 bits for a network portion, and then you had the other 24 bits that were for a host, that Class A network could borrow bits from the host portion in order to create subnetworks. So pretty cool stuff. We're not going to go too far in depth right now. In fact, not much further than this with VLSM, but I would definitely take a look at this online. Go ahead and do a quick Bing search to learn a little bit more and find out more about subnetting. So, all right. On to IPv6, Internet Protocol version 6. This is the wave of the future, and actually it may even be the wave of now for some folks. Not everybody's implementing IPv6 yet, but it will happen very, very soon. Okay. Internet Protocol version 6 is just a new generation of IP addressing. Solves a lot of the limitations with IPv4. The difference between the two is that IPv6 is 128 bits, while IPv4 is 32 bits. And so IPv4 is approximately just 4.3 billion IP addresses. All right, that's the result of 32 bits, whereas 128 bits results in 340 undecillion addresses. And if I wrote out all the zeros in an undecillion, let alone 340 undecillion, I'd be writing for a really long time. I encourage you to look up how many zeros that is. It's pretty cool. And in fact, it's enough addresses to give an address to every single grain of sand on Earth right now. And that is just mind-boggling, absolutely mind-boggling. I had a student tell me once, they did some calculations. They said that not only is it enough for every cell in every human body in the world to have an IP address, but each individual on the planet could also have 500 extra addresses or 5,000 extra addresses for all their devices. I might have messed that up, but I thought that was a pretty cool statistic, whether it's true or not. And so IPv6 addresses, they're represented differently from IPv4 addresses. They're actually 8 groups of 4 hexadecimal digits. And so here we have a sample of an IPv4 address, okay? There's a site prefix, so the first 3 groups, these right here, make up the site prefix. Then we have a subnet ID, which seems much, much, much simpler than our subnets with IPv4, right? Maybe not. And we have an interface ID, which is the actual host portion of the IPv4 address. All of these zeros, they can be condensed using semicolons. just like that, right? So you might see these condensed as 3 semicolons in a row and then 68. So cool stuff. Note here, there are periods for some reason. I must have been making this slideshow really late at night. Right. So how do we get these two protocols to work together? How do we get them to live together? And the reality is that sometimes we just frankly have to use both protocols. And there's a dual IP stack that allows us to use IPv4 and IPv6 at the same time. We're not going to go into great detail on this here, but it's definitely something that you just want to be aware of as you move forward in preparations for the networking fundamentals exam. Okay. We also map we can also map IPv4 addresses to IPv6 addresses. And so what happens is that instead of a normal structure for an IPv6 address with those hexadecimals, hexadecimal characters, the last 32 bits of the IPv6 address are written in just that customary dot decimal notation. And so if you look at this here, we have an IPv4 address that's just written as, it's written with the hexadecimal characters. Note that we got those 2 semicolons showing us condensing, right? And then we just feature the IPv4 address for the last portion of that IPv4 mapped IPv6 address. Okay. So it's amazing what computers can do and how much goes on behind the scenes that we're not even aware of. And so what happens here is that, just to continue on with our discussion of IPv4 mapped addresses, IPv6 packets are encapsulated inside of the IPv4 datagrams. And then with Microsoft, it's done with something called a Teredo adapter, which is just a virtual adapter or sort of a logical interface, a pseudo interface here on the screen is what it says. And an example of these addresses is just located below. So this is kind of crazy, but what happens is we basically take an IPv6 packet and then we just wrap it inside of an IPv4 datagram, send it along, and then that pseudo interface, that adapter, that virtual adapter, is going to go ahead and unwrap the IPv6 packet, and then data is going to move along with processing. Okay. All right, so that's the end of our voyage through the IP protocol. We talked about 2 objectives today. We had 3.2, understand IPv4, and we had 3.3, understand IPv6. We didn't get into a whole lot of detail on IPv6, so I strongly recommend you do a lot of research on your own. I mean, this stuff, you could just learn about it for the rest of your life, and you wouldn't be out of information to learn. So don't be afraid if this seems like it's challenging or if it's hard. It definitely is. And that's part of what makes it so beautiful and so wonderful and so exciting to learn. So thanks again for joining me. I'll see you guys during our next module. Bye. Hi, I'm Cullen. Welcome back to Module 7 of Networking Fundamentals. We're going to go ahead and start detailing today the TCP/IP protocols and using them in the command line. Let's go ahead and take a look at our agenda. We're going to cover objective 3.6, understand TCP/IP, and we're going to do that through protocols, right? And this really is going to detail more so how to use the protocols and what each of the protocols does. I still recommend that you do a lot of intensive research on each of the protocols. Each could be their own course. But that being said, we're going to focus on the command prompts, how to use that, just some basic TCP/IP commands, and then some more advanced commands as well. Okay. All right, so the command prompt. The Windows command prompt, it's just a command line interface. Running it as an administrator is known as running it in elevated mode. You're probably going to hear this commonly. It's not something that you necessarily need to concern yourself with for this networking fundamentals exam, but it is something that you will want to know, especially if you want to take any other Microsoft-based courses. Many tools, tons and tons of tools can be used on the command line. And so let's go ahead and actually just take a quick look at the command line itself. So here's the command line on this computer that I'm working on right now. You see it's real simple. It's the command line interface, text-based. You're not going to see any graphics. It's just text and characters and digits, right? Pretty simple stuff, but very, very powerful still. So, all right, let's roll into TCP/IP commands. We'll start with the basic ones. ipconfig. ipconfig is super useful. It displays the current configuration of your installed IP stack, right? If you use it with the /all switch, it'll give you a lot of additional information. And that's actually what you see here on the right-hand side of the screen. So that is the ipconfig space /all command in action. It can also be used to refresh your DHCP, your dynamic host configuration protocol, and also change domain name system settings. Okay, just real fast, let's just go ahead and see that in action. If I do ipconfig, note here that we had quite a bit of information come up. You can also check your IP address. So here we have just a link local address, right, and a PIPA address, which starts with 169. We do have our IPv6 address as well here. And then we also can see that we're on a Class B subnet. That's pretty exciting stuff, okay? At least for this emulator internal switch, right? We also have our wireless LAN adapter, the local area connection. Media is disconnected there. You can see that we have an Ethernet adapter, our IPv6 addresses here as well, IPv4 address. This is what we're using to communicate on the network and on the internet. And then here's our subnet mask, right? So you can see VLSM is in action here as well because it's not 255, it's 254. Something that we're not necessarily going to detail, but very cool anyway. And of course, look at all these adapters. We just have tons and tons of them available for us, which is great. If I use ipconfig /all, I get even more information. So really, really detailed stuff. Allows us to see a whole lot about our TCP/IP stack. Okay. All right. So let's keep on moving along here. Ping. Ping is another one that you're commonly going to hear people say, "Hey, can you ping me later?" Or, "Oh, I'll ping you." That means that what they're going to do is they're going to send you a quick chat or a message. And computers have their own form of that, and that's why people say, "I'm going to ping you later." Right? What ping does is it verifies IP level connectivity to another TCP/IP device by sending an ICMP echo request message. So pretend that this little message right there, that little bit of data, is an ICMP echo request. What's going to happen is that the other computer is going to send it back, and you're going to see that the connectivity exists between those two devices. Okay. All right. Next is traceroute. And actually, you know what? Let me take a step back here. Let's see ping in action. No better way to figure out how this stuff works than to see it in action. So I'm going to go ahead and copy the IP address for Bing, and we're going to go ahead and ping Bing. Of course, I totally forgot. You can't use Control-V on the command line. You have to actually right-click and then paste. And so check it out. We just pinged Bing, and we sent 4 packets. We received 4. We lost 0. But check out how fast that was. The minimum time was 1 millisecond. Maximum was 2 milliseconds. That's just insane for a round trip. If you don't believe me that we were using Bing, I'm going to show you. So if I'm going to open a new tab so you can see that I'm honest, and I'm going to go ahead and paste in the IP address there. If I hit enter, look at what comes up. Bing. Pretty cool. Pretty cool stuff. All right, so let's go ahead and head back to the presentation here. Next one's traceroute. Tracer T is what it looks like, but we call it traceroute. It determines the path that data is going to take to a destination, typically across the internet or across a wide area network, by sending those same echo requests that we use with ping, but they have an incrementally increasing time to live field value. So there's a little extra data attached to those ICMP echo requests. Okay, we use it to trace the path data takes from sending to a receiving device. So what it looks like is here we have quite a few different routers, right? We have 2, we have 3, and then we have 4. And so what we do is we use traceroute to trace the route by hops that it takes to get from one device to another. Okay? Let's take a look at traceroute in action. And we're going to go ahead and trace the route to Bing. And there it goes. And so it's going to show us all of the different routers that it's going to connect to in order to access Bing, right? So it's going to keep on going here. I'm going to hit Control C to exit out, so that we can go ahead and keep on going with our presentation here, okay? All right, so we talked about some of those basic commands. Let's talk about some of the advanced commands now and get into the nitty gritty. First off is netstat, okay? Netstat's going to display active TCP connections. So any connections that are currently active between your computer and another computer using the TCP protocol, right? With some specific parameters, so different characters that are added on to the end of netstat, or rather additional characters that are provided after a space after netstat. This command can be used to display not just the active TCP connections, but ports on which a computer is listening, Ethernet stats, the IP routing table, IPv4 statistics, and then also IPv6 statistics as well. So let's see that in action really quickly here. Netstat, and I've got nothing. Nope, there it is. So here I've got a couple of different active TCP connections. Oh, there's the rest of them. Pretty cool stuff. Right. Okay. Moving back on to the presentation here. NBTstat is a command that's going to display net BIOS over TCP/IP statistics for local and remote computers. Net BIOS name tables, and then also the net BIOS name cache. If you use it with the -n switch, rather separate it and type NBTstat space -n, then you can go ahead and see the names of all the computers on your local area network that you've communicated with. So if we head back over to the command prompt, let's try that out. NBTstat -n, and look, we have our computer names, right? Pretty cool stuff. NetBIOS responsible for giving a logical name to your computer, so you can call it computer 1 versus, calling it, 192.168.1.10, calling it by its IP address or something along those lines. All right, so back to the presentation. PathPing. PathPing is a command line route tracing tool, very similar to traceroute, except it gives you a little bit of extra information, right? So it combines all the things that you love about ping and traceroute, but it gives you a little bit more info. Okay? PathPing just shows you the degree of packet loss in any specified router, and it really gets in some good detail. It actually will compute results in regards to each hop based on the packets returned from each router that your data visits on its route to its final destination. So really, really cool. It allows you to evaluate things really in depth. All right, let's go to the next one, NSLookup. Right, we display information with NSLookup that you can use to diagnose domain name system problems, and I actually should have problems here at the end. I don't know how that got cut off. Right, so we can use it to troubleshoot. The NSLookup command line tool is available only after you have installed TCP/IP, so you should definitely be familiar with DNS before using this tool, as well as with TCP/IP. And let's actually see if we can use NSLookup on this computer. It's not mine, so if it doesn't work, don't get mad at me, okay? Let's see what happens. So there we go. I do have a default server, and there's the address of it. All right, so TCP/IP was enabled. Good job, Microsoft. All right, back to the presentation. Next, we have NetShell, NetSH, right? A command line scripting utility that enables you to display or modify the networking configuration of a computer currently running. It provides a scripting feature that allows you to run a group of commands in batch mode against a specified computer. That's really it. I strongly encourage you to go ahead and take a look at the NetSH command whenever you have a chance. Once again, take a look at TechNet. TechNet's an awesome resource if you have any questions about any of this information. Okay. All right. The route command. Let's take a look here at our presentation. You can use it to display and modify entries in the local IP routing table. So your computer has a routing table, your local host has a routing table, and you can combine it with the route print command to display the routing table for a Windows machine. This is going to give you the same results as the netstat -r command, but it's a little bit more commonly used. So you can also use it to add and delete static routes. So let's take a look at this one in action. So if we type route by itself, let's take a look at what comes up here. Let me go ahead and go full screen. So there's a lot of really, really good information here. Right, so once again, you use it to manipulate network routing tables. So you can clear all of your routing tables, which I don't recommend. Right, you enforce the using of IPv4. -6 forces the using of IPv6. You also have a couple of different commands like print. Right, so print's a route. Let's go ahead and take a look at print in action since we did mention it. So here's the routing table for your local devices, right? You have different interfaces too that you're printing these out for, but lots of good information. You got your network destination, net mask, gateway, interface. And you also have a metric that's associated with each one. So that metric's used to determine how you route packets on a network. Talk about that a little bit too. And finally, here we have the net command. And although not specifically part of the TCP/IP command set, the net command can display various important networking data, and it does enable you to configure various networking options, such as services. So once again, strongly encourage you to go ahead and learn a little bit more about this command as well. Finally, we do have Telnet. Sorry. Telnet enables you to communicate with remote computers that are using the Telnet protocol. And so you can run Telnet in order to make a communication, or in order to establish communication with a computer. So if I, say, wanted to go from this computer and I wanted to access and utilize, or rather access resources or access this server over here in the top right corner, I can use Telnet to access it, right? You also have a bunch of different Telnet, or rather the Telnet prompt will show up when you're using Telnet, and you can use a bunch of different commands along with Telnet in order to manage a computer using Telnet. So sorry for the redundancy there. A little bit difficult to word this stuff quickly sometimes. All right, so a network administrator is going to use the telnet command with an IP address. So if I went back and I tried to use Bing, use Bing's IP address, I would not have any success with trying to remotely connect to that computer or to the web server, because I'm not going to have the credentials or the authority to be able to access it, right? Typically, Telnet is used with passwords and usernames, and so it's just really important to keep that in mind, that you're going to need to actually have the credentials and the authentication values to be able to access a device remotely using Telnet. Another thing to keep in mind too is that Telnet is frankly just an older, out-of-date protocol. And so we've actually switched over to something called SSH, Secure Shell. And so we use that now instead of Telnet, but Telnet is still in use, and pretty widely so, if I'm not mistaken. I actually teach it to my students still, so if you're learning it, feel pretty good about that, okay? Still important stuff to know. All right, so that's the end here. Objective 3.6, understanding TCP/IP through the command line. We talked about the command prompt, showed you some basic TCP/IP commands, and discussed a couple of advanced ones as well. Once again, strongly suggest that you go ahead and take time to do your research with these commands and actually take some time to use them. Experimentation is the best way to learn sometimes. Just remember not to break anything, and if you do, it's not my fault. Thanks again for joining me. I'll see you soon, okay? Bye. Hi, I'm Cullen. Welcome back to Module 8 of Networking Fundamentals. We're going to talk about networking services. Let's go ahead and jump right into the agenda here. We're going to cover two different objectives today. We've got understand networking services, and we'll detail common network services that are available. And then 3.4, understanding name resolution. This is one of my favorite topics to discuss. And we'll just go over the name resolution techniques that are available, okay? All right. Without further ado, common networking services. So DHCP, or Dynamic Host Configuration Protocol, is the protocol that enables our computers to obtain IP addresses automatically. And so the IP information obtained is probably going to include your IP addressing information, your IP address itself, a subnet mask, a gateway address for your default gateway device, the router, and then your DNS server address. We'll talk about what the domain name system is in detail here in a little bit. And then there are some other advanced features and options as well that can be included with DHCP. The server definitely provides a really reliable IP address configuration, and also too, it makes it really, really easy for network administrators, because frankly, I certainly wouldn't want to assign an IP address every time that a device connected to the network, not with however many devices there are now in existence on any given network too. So, all right, so let's talk about the DHCP server and how that process works. It starts leasing an IP address to client computers after the following steps are performed. And so you see the steps there. Clearly, you have to install the DHCP service on a server before it can be used. You configure an IP scope, activate that scope, authorize the server, and then configure any other advanced options. And of course, those are optional, but if you're a really good network administrator, you're probably going to be configuring those advanced IP options. I honestly probably am not there yet myself, but someday, right? All right. Let's talk about DORA. So DHCP sessions, when they begin, they use a four-step process known as DORA. The first step in this process is discovery, and that's where the client sends a broadcast to the network just simply to find a DHCP server. So note here, it says, that computer says, hey, are there any DHCP servers here? That is the discovery process. And whoops, doesn't want to let me have my marker. That's the discovery process, right? Next, that server is going to respond, and it sends a unicast message offering an IP address to the client. Then, of course, we have, so I'm going to check these off as we walk through them. We have a request where the computer says, hey, I would really, really like that IP address. Please send it over to me. And then the DHCP server sends a final unicast message to the client that includes the IP information, right? So there's ACK is short for acknowledgement. That's where it is. Quick little point too, and I know that we discussed this in a previous slide, DHCP, just like most protocol, well, just like all protocols, apologies there, all protocols is going to use ports, a port, specifically ports 67 and 68, okay? All right, so we talked about APIPA a little bit earlier as well. APIPA is another service, a networking service that makes things really nice for us. It assigns that unique IP address that starts with 169. When no DHCP server is available. And so APIPA, though, can cause us some troubles too, because if you have an APIPA address, a 169 address, then it makes it difficult for us to obtain an IP address properly from a DHCP server sometime, right? So when a client attempts to obtain an IP address, the DHCP server might be too busy or some other issues might come up. And so it will prevent a computer from accessing the internet if you have one of those addresses. But the good news is that you can use it to access and communicate with other devices on your local area network. Next up, we'll just touch on this real briefly, remote desktop services. These are super useful so that you can access computers remotely across a network. And so we use remote desktop services to enable a virtual desktop infrastructure. And so this is just session-based, so we're able to access it. We can log into a desktop remotely and then start a session and then end a session, right? We can use its applications. We can basically work from anywhere if we use something called a thin client, right? It's a type of computer that doesn't have a lot of resources and intense hardware, right? It's thin. But we're able to use those computers because we can just connect to servers that run remote desktop services, which enable remote access. So, all right. Next, and this is one of my favorite topics, name resolution techniques. I love talking about DNS. I think that this is super fascinating. It's a worldwide service. Domain name system is just a worldwide service that resolves host names to IP addresses. So if we have www.bing.com, we can go ahead and resolve that to an IP address, and vice versa, right? It does translation. DNS architecture is just hierarchical and distributed, and it has an associated set of protocols that define a mechanism for querying and updating a database. It has a really extensive database that aligns names with IP addresses, and that's very similar to like a telephone book that aligns telephone numbers with names. And of course, for some of you, you may not even know what a telephone book is because those are starting to go the way of the dinosaurs. But let's look back at our slide here real fast. DNS is part of TCP/IP, and then the servers are going to use inbound port 53 to accept name resolution techniques. Okay. I want to touch back real fast on hierarchical and distributed. Okay, what this means is that there are a bunch of different servers, and some have greater importance or more so importance than others, right? So they're hierarchical, so others have greater powers, I guess you could say, than others. They're higher on the food chain or lower on the food chain. Lots of different ways you could talk about it. But when you type in an address like bing.com, there's actually an invisible period on the end of com, and that actually points you to the root server, right? And then below the root server, we have a .com server. And next to the .com server could be like a .net server. And all of these servers know the location of maybe like the server or the DNS server that's used for Bing. Right? So pretty cool stuff. We'll detail that here in just a second. All right, so how does DNS work, right? So what happens is you have a client So I forgot my desktop icon, so I'm going to draw my funky little laptop here. And it's going to try to send its request to a name server. It's going to do that through a device called a resolver. Our clients through the resolvers are able to access forgive me, I just messed up in my speech. Clients access resolvers, which are libraries, and then those libraries perform DNS queries. They do so by making recursive queries to name servers, right? And this name server might be located at your internet service provider, somewhere locally close to you. And so that resolver expects to see a response with either the destination IP address, like the IP address for Bing, or an error message saying, I cannot find this this IP address for this specific name, okay? Now, what happens when the resolver goes to work, it expects that response, and it tries to get it from the name server. The name server might go do some work in the background, and it actually embarks on making some iterative queries. And so what happens first is if the name server doesn't have the address, the IP address, in its cache file, or really, which is like the phone book reference that I made earlier, it's like a phone book, then what it's going to do is it's going to go ahead and send an iterative query to the root name server. The root name server may have the address. If it doesn't, it's going to tell it where to go, and maybe it tells it to go to the COM server. So we went here, the name server says, no, I don't have it, but I can tell you where to find the COM server. Well, then the COM server sends back perhaps the IP address. And then we just skip straight to step 8. The resolver then sends us back the IP address, and all of a sudden, here we are. We have Bing on our screens. Okay. Let's talk about WINS. WINS is another name service that's available to us. It resolves the net BIOS names, right? Those logical names that our computers have to IP addresses. WINS is required for any environment which uses net BIOS or where any of our devices have net BIOS names. And it's just Microsoft's version of the net BIOS name service, right? It's combined with the name server. So WINS and DNS, they're both name resolution services for TCP/IP. Pretty simple to understand. But still a lot of complexity involved. So do take your time and take care in understanding and learning this information. All right. So that's it for this module. Just a quick recap. 3.5, understand networking services. We talked about common networking services, and we also talked about different name resolution techniques with DNS and WINS. Hope you guys enjoyed it. I know it was a pretty quick one. Thanks so much. I'll see you next mod. Hi, I'm Cullen, and welcome back to Module 9 of Networking Fundamentals. Right now, we're going to talk about wide area networks. All right, let's go take a quick look at our agenda. We're going to cover 2 different objectives today. We're going to talk about routers, how they work, and more specifically about static and dynamic routes, so the paths that data can take across the internet and across networks. And we're going to talk a little bit more in depth about wide area networks. The internet, of course, is the mother of all wide area networks. It's huge, but we'll focus on what wide area networks are, and then also talk about a few common connection types that you should be aware of, especially if you're heading off to take the Networking Fundamentals exam. So without further ado, static and dynamic routing. First off, a router, right? What is it? What does it do? It's just a central connecting device that uses TCP/IP routing protocols to forward packets. They use IP addresses like we discussed. It's a layer 3 protocol, right, IP. And routers connect local area networks to each other. And they allow communication between hosts on different networks. And so you see here with the bolded connections, let me bring up my pen real fast, that routers route data along pathways, right? Routes. And they enable communications between 2 different devices. And data can actually take a bunch of different routes. That being said, it can also take the same route every single time. But we'll feature that here in just a second. Routers have routing tables, and they use the information in these routing tables to make educated decisions about how we route from one host to another, right? So how we send data across a network or a wide area network, as we're about to learn in a little bit. Routing tables, they contain just a list of paths to various networks, and they can be configured manually or automatically. If they're configured manually, it's known as static routing, and automatically, it's known as dynamic routing. Okay. All right. To your right is an example of static routing. What's going to happen is every single time when you send data from your device here to this server over here, is going to follow the same exact route. Now, the server, if it sends data back to you, may not necessarily do that. It may be configured for dynamic routing and not static routing. So keep that in mind. A static route, clearly just a fixed path. I really want to emphasize that, right? It's definitely a very, very fixed path. So data is always going to travel down that fixed path. One thing that's really important to note about static routing is that if any links or any hops happen to go down, then what happens is you can't send data to that destination anymore. The route is just simply unavailable, and that means that it's not fault tolerant, which can definitely cause you some problems. Okay, so let's go ahead and take a look at the slide for dynamic routing. Oh, I feel like everybody needs to watch that animation again. Hold on just a second. Wait for it. There it is. Dynamic routes. Routes change, right? Dynamic routing allows a router to detect when brand new routers are connected. And this means that the new pathways are available for sending packets. And so routes are then added to the routing table dynamically, right? So they're just automatically updated. That's what dynamic means, right? Automatic, just adjusts. This type of routing is fault tolerant because what happens is if you have a connection that goes down, maybe you have like 3 connections that go down, right? Guess what? I can still send my data down a pathway to the server. So dynamic routing, super helpful, always aware of the best place for us to send our data when we're moving from router to router. It ensures efficiency, fault tolerance, and just effectiveness of the internet as a whole. The dynamic configuration of a routing table isn't possible without protocols. And protocols, of course, are our favorite things because they make sure that the internet functions. There are a few different protocols that you need to be aware of for dynamic routing. You've got RIP, Routing Information Protocol, OSPF, which is Open Shortest Path First. It's a protocol that monitors a network for routers. And it'll adjust the routing table based on when the link state of a router goes on to off to on, and so on like that, right? So it always is aware of which devices are on in a network. Then you have IGRP, the Interior Gateway Routing Protocol. And you also have Border Gateway Protocol as well. Definitely do a little bit of research on each of these protocols. Know that there are things called distance vectors that you should be aware of. And what that is it's just a calculation. It's essentially a metric that's used to determine which route should be used to send packets, right? So some routes are better than others. Just like if you're trying to make sure that you get across the bridge during rush hour. Sometimes it's better not to take the bridge. You don't want to take the route that might be the most direct. Sometimes it's better to go around. And so just like us being dynamic in our cars and our vehicles, or even by walking or taking the bus, sometimes we reroute ourselves in order to make sure that we get there in time. So our data is no different, okay? Let's go ahead and go back to the slideshow. Just a real quick review on routing tables. In larger networks, storing information in routing tables requires a lot of memory. And so just more entries means more memory. And the number of entries stored will dictate how routers and routing protocols are used, or rather, which ones are used. And so there are a lot of different factors that will go into how we set up routing on our networks. Okay. All right, so let's talk about wide area networks and what they are. First off, the internet is a wide area network. Wide area networks, they just connect multiple local area networks over large geographical regions. And so what you would see here on this slide, if these were connected, is you might have routers that sit at the edge of each of these local area networks, right? And they may be connected in a mesh topology in order to make sure that each of these local area networks are able to communicate. And of course, those routers would all be connected to our switches, right? The internet, the largest WAN in the world. All right, and the internet in general, LANs, they use a technology called packet switching. And packet switching means that the data is broken into small segments, and then addressing information is added to each segment in order to make it a packet. And then from there, routers transmit packets across networks from one LAN to another, right? When packets arrive at their destination, they're simply reassembled by walking through the communications subnetwork, the OSI model, and they're reassembled into the wonderful, beautiful imagery and data that we see on our screens. Examples of packet switching protocols that you should definitely be aware of for this exam are X.25 and also frame relay. All right, so let's talk about the different kinds of connection technologies that are available in WANs, right? So how do we access the internet from our home or from our office? What kinds of technologies are available to us to connect to all that data out there? So first up is T-carriers. A T-carrier is just a telecommunications carrier. It's a cabling system that transfers data at high speeds. It's a dedicated line, right? So if you have a line lease from a T-carrier, you're going to have some pretty high transfer speeds. There are two common carrier systems. There's T1, which is also known as E1 in Europe and J1 in Japan, and then T3, which is known as E3 in Europe and then J3 in Japan, respectively. These are private lines between LANs, and sometimes you might find different offices using T-carrier systems. So, all right, next up is ISDN. ISDN is just a digital technology that's developed to offer faster communication speed than an analog telephone line. So telephone lines, of course, if you ever had a dial-up modem, they weren't very fast. It resulted in just painful download speeds. But it's just ISDN is a communication standard enabling it's a set of communication standards that enable simultaneous digital transmission of data, fax, voice, and video. And so another way of putting this is that it's a converged network because all those services are offered on the same line. And I may have not said it aloud, and you probably see it on your screen there, but ISDN stands for Integrated Services Digital Network. All right, next up is the Fiber Distributed Data Interface, or FDDI. It's a standard for transmitting data on fiber optic cables at a rate of around 100 megabits per second. The cool thing about FDDI is that it supports transmission beyond 50 miles, and it's also it's the original FDDI standard called for a physical double ring topology. I honestly wouldn't even know how to draw that specifically right now. So definitely go ahead and give that a quick Bing search. FDDI is primarily a protocol used on backbone networks. And something that I think is really interesting is backbone networks just in general, period. That's where all data is being sent across the internet at super high speeds, right? So the internet is a really, really complex system. It's got a very complex infrastructure, but the backbone is where things are being sent back and forth at its fastest, right? It's the reason why we can send a ping and get that back in just a millisecond, or why we can go ahead and send a DNS request across the globe and perhaps access a website in just nanoseconds. Like, it's absolutely insane how fast the internet can be and how fast networks are. Okay. All right, next one up, we'll go ahead and detail a new communication technology. The digital subscriber line, or DSL, is just a family of technologies that provides data transmission. It uses local telephone networks to do so. And so voice and data can be run over the same line. Just uses a higher frequency band to transmit data. So you've got 3 different varieties of DSL here. We have XDSL, we've got ADSL, and then SDSL. Right? Make sure you're aware of all of those different varieties as you're studying for the exam. All right, broadband cable. This is where we use, it's broadband cable is just used for cable internet and cable television. This is probably what you have in your home, right? I have it in my home. It operates at a higher speed than DSL, and the rates can range from 384 kilobits per second to 20 megabits per second. So that's a pretty common network speed for a home internet. So this is something that you're probably using right now, and you may not even realize it until now, right? Because I just told you. Cool. Last technology that we're going to talk about is POTS, which is a plain old telephone system. So I don't even use the telephone system anymore. I have a cell phone, and so I use a cellular network. But the POTS system is what we use for regular phone lines. It's been around since the 1940s. It's now digital, but it used to be analog, and it also depended on something called circuit switched technology, where you had a dedicated line. And so if I picked up my phone to call somebody, and then somebody else in the house picked up another phone, then what that would mean is that that person holding the other phone in my house would hear everything that I was talking about with my friends or my family or maybe my girlfriend at the time. It was always really embarrassing. Anyway, that's it. That's all we got for this slideshow. Let's do a quick review of our agenda here. We talked about just routers, static and dynamic routing in general. We also touched on what wide area networks are, as well as some of the connection types that are featured in wide area networks that help us communicate. So that's all I've got for this mod. I'll see you in the next and last one. Thanks so much for joining me. Take care. Hi, I'm Cullen. Welcome back to Networking Fundamentals. This is our 10th module and our last module. We're going to talk about the internet and all of its glory. Well, actually, just some of its glory, but you know what I mean. Anyway, let's get going, okay? Let's take a look at our agenda for today. We're going to talk about understanding the concepts of the internet, intranet, and extranet. That's the very first objective for the Networking Fundamentals course. Save the first for last. I guess it should be the best for last, but this is just the first for last this time, and maybe the best, who knows. But we're going to talk about the internet, intranets and extranets, virtual private networks, and then we're also going to talk again about security devices and zones. Okay, let's get it going. The internet. So what is it, right? It's not a cloud like you see it represented in pictures. It's actually just this worldwide, amazing, impressive system of connected computer networks, right? Just tons of WANs, all interconnected. Devices connect to the internet using the TCP/IP protocol suite and all of its protocols. And the internet contains a lot of information, resources, and services. You, like me, are probably always using the World Wide Web to either access or host content. You use email all the time. And it also, the internet provides connectivity for peer-to-peer networks and for file sharing. just a really, really cool invention. So thank you to those who invented the internet. With that being said, what's the World Wide Web? Well, the World Wide Web is also another enormous system of interlinked hypertext documents. So everything that we access on web pages use a markup language called HTTP, and that's sent back and forth between browsers using hypertext transfer protocol, along with some others now. But it basically involves anything that can be sent and accessed using a web browser. Interlinked hypertext documents, they contain text, graphics, video, just a ton of really cool stuff. I strongly suggest that you check out the HTML5 application development course if you're interested in learning more about the World Wide Web and how to build and design web pages. Okay. Currently, the World Wide Web's in stage 2.0, so it's known as Web 2.0. 2.0 is an interactive type of web experience compared to the previous version, 1.0. I kind of wonder what I was thinking when I wrote that. I'm like, does that mean that 1.0 is not interactive? I don't know. Anyway, let's keep moving along and let's talk about intranets and extranets. All right, so an intranet is inside of the internet, right? So an intranet is a private computer network or a single website that an organization implements in order to allow its employees to access data around the world. Employees have to log in using a username and a password. That's authentication, just verifying you are who you say you are, before somebody can access information located on an intranet. The whole purpose of this is to keep the general public out and away from files and data sets that should be exclusive to a company or an organization. Companies and organizations can then add extranets as an additional layer outside of the intranet. So an extranet is very similar to an intranet, except that it's extended to users outside of a company or organization. So you could have a sister company. Maybe let's say you have company A and you work a lot with company B. You can give company B's employees access to your extranet, and that allows them to access important files, but still not access your intranet. User authentication, still super necessary. Whoops, let me pop back in that slide. I meant to go ahead and select a color here. Authentication is super necessary. I'm gonna use my laser pointer, my pen won't come up. Because the extranet itself still shouldn't be open to the general public. Not anybody, not just anybody, should be able to access an extranet. So we covered a couple of different ways that if you're working for a company or an organization, how you can access data, right? So intranet, just to review, is for internal employees. An extranet is for partners. And then you might have something like a web server that's for the public, that's located accessible via the internet. Let's talk about virtual private networks. So what do you do if you are working from a remote location? Maybe your company's based in Seattle, Washington, and you happen to be working out of Shanghai, right? Well, you can access your company's intranet using a virtual private network. And that's just a virtual connection between two or more private networks. It allows users to access resources remotely. They're going to log in using a remote access protocol. And VPNs do this by simply encapsulating, or rather creating a tunnel in which communications can pass through, right? So the tunnel goes through all the different LANs and WANs that data communication might have to pass through in order to reach its destination. So you could be working remotely over here with our remote users, right? And maybe you're over in Shanghai and you want to go ahead and access this server that happens to be on your company's intranet. Well, you just go ahead and create a tunnel that follows directly through until you get all the way to this router right? And then access the server from there. Okay. VPNs use data encapsulation and encryption to ensure that the data is secure. That's also something that shouldn't be glossed over. Okay. When we implement VPN, we have a couple of different protocols that allow us to do it. Point-to-point tunneling protocol is the first one. It was the original protocol that was used. It encapsulates frames into IP datagrams. The data isn't encrypted by default. It still is the most commonly used VPN protocol, but it's really important to note that it's less secure than the protocol that we're about to talk about. The layer 2 tunneling protocol with Internet Protocol Security. L2TP and IPsec is just a combination, actually just L2TP itself is a combination of PPTP and layer 2 forwarding. It's not actually that secure by itself, but when you link it with IPsec to encrypt the messages, it becomes much more secure than PPTP. So keep those things in mind. Those may appear on the exam. Definitely take some time to study both of those protocols and get them down. All right. Lastly, we'll talk about security devices and zones. So if we want to access these networks, we want to protect our data and make sure that it maintains its integrity and that other people aren't able to steal it and access it, we've got to make sure that we're set up to properly protect it. So to do that, we use security devices such as firewalls, right? They are the main defense for not just a company's network, but for any network, whether they're LANs, WANs, intranets, or extranets. We can also configure routers and switches to perform security functions like traffic filtering in order to prevent unwanted communications. We can also set up perimeter networks, the demilitarized zones. We talked about those a little bit earlier. They help keep open specific information that you want to make available for public users while making sure that you keep people out of your organization's data, right? That private data that you want to keep private. Firewalls, as we mentioned before, they protect a network from malicious attacks and unwanted intrusions. They inspect communications for malicious data, and they also perform filtering of data in order to make sure that if they do find something that's malicious, that it doesn't get into your perimeter network and even into your local area network, right? Whether it's an extranet, an intranet, or just a LAN, right? Just a plain old simple LAN. Something that's cool to know about firewalls is they can actually be implemented as software or hardware. There are devices that are dedicated firewalls, and then there's software that can be run on a server or even on a local machine in order to filter out traffic and inspect for malicious data. Another thing that's really important to know is that firewalls are pretty ubiquitous. They are everywhere. They're the most commonly used type of security device, and you will almost always find them on an organization's perimeter, right? And here in this particular example, we have two right here, right? So we've got these two guys up here at the perimeter and then also protecting the LAN as well. All right. And just to quickly recap what a perimeter network is, I know that we already discussed this in a previous module, but a perimeter network, once again, is just a small network that's set up separately from a private local area network and the internet. Sort of sits in between a local area network and the internet more specifically. And this allows users outside a company to access specific services located in the demilitarized zone. They might house a switch with servers that offer web, email, and other services. So just a couple of things to keep in mind there. But this is also a great way to secure your data while also maintaining and providing access to others to important services. All right, ladies and gentlemen, that's it. This is the last one. Just to do a quick recap, we discussed the objective 1.1, understand the concepts of the internet, intranet, and extranet, detailing the internet, the intranets and extranets, what they are, how they function, who uses them. We talked a little bit about virtual private networks, and then finally security devices and demilitarized zones or perimeter networks. So thank you so much. I hope you enjoyed learning all this stuff. I know there's still a lot more to learn. Definitely gonna have to do a little bit of Bing searching and you know, a whole lot of reading and probably some video watching too. But thanks again. I really enjoyed our time. That was Networking Fundamentals, and I'll see you later. Bye.